James, I have a question. So when you finish, is there time for Q&A?
Yes.
So
It goes for 40 minutes. There's roughly 5 minutes for Q&A.
okay, so I'll. Hello. Yes. Hello. Hi, everybody. How's it going? Good? Oh, come on. If you have no voice, James not going to come up and, talk about his talk. How it's going? Good. Okay. It's a 10 years DDD. This is my probably fifth time. I don't know. I lost count. But welcome to room 1. This is the best room ever because it's sponsored by Microsoft. Somebody made me say that, but it was not me. Don't hate me for it. Okay, so the session James going to be talking about is creating game engines surprisingly simple, and I am actually excited for this. James Morgan, he's going to be our speaker for this session. He's a full-stack senior consultant at Insight with a passion for all things game dev. Welcome, James, please.
Awesome, thank you everyone. So today I'll be talking about crafting your own game engine and how it's actually surprisingly simple. So first thing, just a bit about me. I'm a senior consultant at Insight. I'm also CEO of my own startup, Pot Pirate, which is a cray pot theft prevention. And I'm also passionate about all things game dev. Firstly, I'd just like to thank all the sponsors of this event. Without you guys, it wouldn't be possible. And a big shout out to Microsoft for being the room sponsor. So we're going to cover a few things today. We're going to cover what is a game engine, some modern game engines, the architecture of the game engine, run you through the simplicity of an engine, using the facade pattern, practical tips for getting started, some pitfalls, best practices, and then a Q&A at the end. So what is a game engine? Well, the official definition on Wikipedia is a game engine, also known as a game framework, is a software development environment for people to build video games. This is a nice definition, but it's a bit confusing. I think it can be a lot simpler. A game engine is a set of reusable libraries that can be glued together to build a game. So what do I mean by this? This means that it could be as simple as just a bunch of reusable classes that you write, for example, a math library that you share throughout your games. So what are the roles of a game engine? Well, it serves a few key roles. The main one is platform abstraction. This means that it shouldn't be relying on being a Windows-specific, Mac-specific, Linux, mobile, or desktop. The other one is it should provide reusable libraries. This means that the libraries, such as your physics engine, rendering engines, or math library, should be reusable without tight coupling. It should also provide development tools. This is for the game developers and artists. They want to have an easy time developing the game, and they want to focus on the game itself and not the tools. So what are some modern game engines out there? Well, right now, one of the most popular ones and gaining traction is Godot. This one's super popular as it's open source, community-driven, versatile, and very lightweight, coming in at under 100 megabytes in size. So very easy to install and run. Another popular one is the Unity engine. Unity is very popular for small to medium-sized games, and it's widely used, again, quite versatile and has a robust toolset. This is more on the 10 to 20 gigabytes in size. Another is Unreal Engine. Now this is if you want AAA studio quality games. It has a robust toolset, it's closed source, and it's again widely used. This is mainly used by a lot of AAA studios such as EA. This is in the 50 to 100 gigabyte size. Going into proprietary engines, there's two that I can think of that are the most sort of out there. The first being Frostbite, and this is done by DICE EA. They use this for all their games such as FIFA and Battlefield. It's very high performant and focuses on realism. The other is Rage, Rockstar Advanced Game Engine. This is the one used for all GTA games and Red Dead Redemption games. This focuses on realistic worlds, AAA quality, and high fidelity tooling. If you've ever seen any of the GTA games, you know they're quite open world and has a vast graphics engine. So what about a high-level overview of what an engine looks like? Well, this diagram here is by Jason Gregory, and it's the architecture of a game engine. This is a very confusing and very small diagram, and that is the point. It's meant to scare you and think that game engines are hard, but they're not. This is really what your core systems will look like. You'll have a sound engine, a math library, a physics engine, a rendering engine, and some sort of window management. Now, the core ones that you would need is your math, physics, rendering, and window, and sound is something that you'd want if you want a polished game, but maybe not necessary. On top of these core systems, you're going to want some sort of gameplay systems. So this would be your scene management and entity management. On top of that, you might want to add in scripting, an editor, terrain, AI agents, and multiplayer, for example. These are what I refer to as gameplay systems. So they're not core to the engine itself, but they're nice to have to be able to build a game. So what about the simplicity of a game engine? You might be thinking, this is still quite a lot and it's confusing and that's not very simple. All those systems aren't very simple. Well, at the end of the day, a game engine is just a game loop. And what is a game loop? It's essentially just something that continuously runs while you're playing the game. For example, you might apply forces, resolve collisions, render, and then handle input. And it will just continuously do this until you exit the game. So what does this look like in code? Well, up here, we have a very simple game engine loop, which will basically run a window and render some text on the screen until we're done. So we're going to jump into building a demo here, and what we're going to be building by the end of this is a very basic bouncing ball, which you can call the start of your first game engine. So moving into some code here, I'll just go to the next slide, is we're going to be drawing a canvas first. So this is your window. So you might be wondering, we want to build a ball, so how do we build that? Well, the first step of this is to have your begin draw, have your clear background, and then draw a circle. This draw circle takes in a position and a color and a radius. You might be wondering though, this still isn't really a bouncing ball. It's a red dot on a screen. So how do we get it to bounce? Well, to get it to bounce, we're going to introduce something called a ball struct. This will contain the position, velocity, radius, and color. And this will act sort of like our data for the game. In the code itself, once I transition to here, we're going to first set up a window, set the target FPS. We want to set the target FPS to 60 as using a really nice library called Raylib. The frame depends on the physics, so if you set 240 FPS, all of a sudden your ball's going to fall really fast. We want to add a fixed sort of rate. The first thing is we set an initial velocity and position. So we set that to the center of the screen using a vector. Next, when we create the ball, the first thing we want to do is first apply forces to that ball. And this is where we increase the velocity by a vector constant. We then begin drawing and draw the ball. And this looks something like the following. We start the ball and it will just fall to the floor. So, it's still not bouncing, right? Like it's a ball, but it's not bouncing. So how do we get this bouncing? Well, for this, we're going to introduce some very simple collision detection and resolution. In this code here, essentially all we do is after we've applied the position to the X and Y, on line 36, you'll see that we check the ball's position. If it is greater than the screen width on either side, then we invert and reduce the velocity by 40%. And then if it's on the top or bottom, which is this line here on 50, we will reduce it by 10% for the top and bottom. The reason for this is we just want it so it hits the sides, it'll reduce velocity faster, and will come to a stop sooner. So what does this look like? Well, now we have our bouncing ball, and you might be thinking, well, this isn't really a game engine. You've just drawn a bouncing ball on a screen. And this is where we get to refactoring time. We can refactor this to look more like a game engine doing the following. We'll create a few methods such as create ball, draw ball, update ball, and check ball collision. Now, in our code, when we go here, you'll see a pattern starting to emerge. The first thing we do is we want to apply forces to a ball. The next is we want to check collisions on the screen edges, and then we draw a ball. So this is starting to look more like a pattern that you could reuse to draw more than just one ball. This leads me on to engine schedules. So what are engine schedules? These are the schedules in which your game executes. The first being your pre-initialization, then your initialization, post-init, your game loop, and then your exit. The ones I want to focus on are the ones in your game loop. This would be pre-update, tick, update, and post-update. Now, pre-update is something that you want to happen at the start of every frame. This would be updating your delta time, clearing your renderer, and doing some basic scene management. The next would be tick. Tick is where you want to put all your game logic, physics, and AI and state updates. The reason for this is tick does not run every single frame. Tick will run at a fixed time step. For example, 60 Hertz. This means it'll run at 60 frames per second. It must be independent from your window and renderer, and this is so that your physics engine code isn't using all your CPU cycles. The same goes for game logic. If you have your game logic running every single frame, you're going to constantly get frame lag, and it's not going to be fun to play a game. The next is update. This is something that has to happen every single frame, and if it doesn't, then you're going to get flickering. This is where you would do rendering, handling input, and do camera and GUI. Now, rendering, if you don't do every single frame, it's going to flicker, and input handling is an interesting one. You may or may not know that when you press a key press, if you don't handle it in that update frame, then it will be ignored. For example, if I did my input handling in the tick and I pressed a key and it happened between my two ticks, then it wouldn't be registered. And this is just how the event system on your computer works. The last is post-update. So this is something that has to happen at the end of your update frame. The most common for this is doing your window update, so swapping the frame buffers around and doing some sort of render post-update and cleanup of your entities. The most common approach of this is implemented in OOP. This is where you would have an iSystem interface with all of the methods for each schedule. This is a super common approach, easy to implement, and quite robust. The other is the functional programming approach. Now, this is where you have your schedules as an enum. You have a function that you pass in that takes the engine as a reference into the parameters, and then you have your engine itself. The way this works is you would have an add system function on the engine, and this would take in the schedule and the method. The reason it has to have the engine as a reference is that because it is a functional approach, it doesn't have any sort of dependency injection or idea of what a class is. So how do we implement this? We're going to implement schedules using OOP. In our code, we have the iSystem. Now, the iSystem has a few things in here. It has the pre-init, init, post-init, pre-update, tick, update, post-update, and exit. And this is in C++, so the syntax might look a little confusing if you're not used to it. Essentially, C++ doesn't have any interface like Java or C#, so you've got to implement it using abstract classes. Next up, we would implement a window system. Now, this window system is where we're going to handle all our code for the window using raylib. So this is where we initialize our window and set the target FPS in the pre-init. Now, we don't want to do anything in init, post-init, or tick. So in pre-update, we're going to begin drawing and clear the background. And then at the very end of the update, we're going to draw the FPS and end drawing. And on exit, we're going to close the window. The other one is we're going to create a ball system. Now, this takes in the ball structure again and the gravity constant and creates a set of balls, which you can see on line 60 here. This is a vector of balls. In most languages, this would be an array list or a dynamic array, whatever you want to call it. In C++, they call it vector. So we're initializing an array list of 60 balls, and then in initialization, we are creating each ball with the create ball method. Now, this create ball method is slightly different to before. it does contain logic for randomizing the position, velocity, radius, and color, and you'll get to see why in a second. The other is tick. So during our tick frame, we want to loop over each ball in the array, and then we want to call update ball. And this is the same as before in that it'll simply update the velocity and position of the ball. Now, once we've updated the ball's position and velocity, we then want to loop over each ball and check for ball collisions. It's important to note that you need to do this in a separate loop, as if you don't, your physics code won't be deterministic. In our check ball collision, we do the same thing about checking the screen edges and reducing the velocity. We then also have code for checking between other balls, and I won't go into this code as it's not a physics demo, but it is available on GitHub if you want to go into it later. Then in the update, we do an update loop, again, looping over each ball and drawing the ball. So just looking at this tick, you might see why you wouldn't want to run this every single frame, because if you ran this every single frame, you've got 2 loops iterating over your entities, so to speak, and this would cause a lot of lag. So moving on to main, you'll see that now it looks a lot simpler. We now have a shared pointer to an I system for our window and ball system. For those not familiar with C++, this is essentially a reference to your interface, and it's using smart pointers. We then have our array list of systems, our window system and ball system. The order in which they are added shouldn't matter. However, if there is a specific order, for example, you might want to have a renderer at a specific order, then you can. Then all we do is we iterate over each system for each step. For example, we iterate over all the systems for pre-init, we iterate over all the systems for init, post-init, and so on. Then, once we enter the game loop, we run pre-update for all the systems again, tick for all the systems, update, and post-update. Now, this is a fundamental flaw of the OOP approach, is that you have to iterate over each system and call them even if those methods don't exist, whereas with the functional programming approach, you would only call the functions that are needed. And then on exit, we run that. So now I'm just going to run this demo here, and you'll see sort of what the output is. So we have balls bouncing on the screen. The physics resolution isn't the best, so there's quite a bit of jittering going on. But that sort of, this example runs through, what your entities would be, in this case balls, and sort of how you would create your first steps towards an engine. One thing I'd like to highlight again, just in the ball section, is how these balls are wrapped up in a structure called ball. There is no update methods or any sort of methods on this structure. It is purely data, and this is sort of the data-oriented approach to game engines. And so moving on from that, again, that was just our bouncing balls, is we'll move on to the entity component system. So an entity component system is the data-oriented design approach to building your entities in a game engine. So what is an ECS? Well, entities are just IDs. Entities don't store any data, they don't store any methods, they are just IDs and point to something. For example, your entity might be ID of 0 and that's all it stores. How do you store your entities though? Well, this is what you use an entity list for. So this would be an array or dynamic array of IDs. The most common approach is to store entities in the order in which they're inserted in the entity list, for example, 0, 1, 2, and 3. Then you have components. Now components, again, they're data-oriented by design and they only store data. This means that your rigid body and transform component don't have any methods attached to them, such as resolve collisions or check collisions. The example here is we have a transform component, which is used for your position, rotation, and scale, which stores a vector, quaternion, and another vector for scale. Then your rigid body would have a mass, center of mass, force, and so on, whatever data it would need for your rigid body. And these are stored in a contiguous array. So this is designed to reduce CPU cache misses. Essentially, each component is stored in a bucket, for example, a rigid body bucket or a transform bucket. And anytime you want to iterate over these components, you grab the whole bucket and it's stored in your CPU cache. This means that if I want to iterate over my entities with rigid bodies, I don't have to search in the RAM every single time I want to grab a rigid body, as it's all stored there in the CPU cache once you grab that first rigid body. So reiterating, entities just point to components. They are just an ID. For example, you might have an entity that points to a transform model and rigid body, or one that just points to a transform and script, for example. Your systems don't actually care about entities. The systems actually just transform the data. So for example, your physics system would only take the data from the transform bucket and the rigid body bucket and then transform the physics engine based on that. As well, your rendering system would take the model data from the models bucket and the transform data from the transform bucket and draw your models where the position is. And then you might have some, such as a script system, that just takes one component list and iterates over those. So your script would then just iterate over the scripts and nothing else. And this is what it looks like all put together. Your entities point to data and systems transform that data. So building a monolithic game engine, what does it actually take to build? Well, unfortunately, you are going to need all of those core systems, and especially a sound engine if you want a polished game. So you're going to want a math library of some sort that is shared between your physics, rendering, and window, and then you're going to want a physics engine for realistic physics, a rendering engine to render to the screen, and some sort of window management. You're also going to want some gameplay systems. Now, if you don't have these gameplay systems, such as a scene management or ECS, then it's going to be pretty hard to build a game. Some really nice ones to have as well would obviously be an editor that makes your engine feel feature complete. You want some debug tools, you might want AR agents in there, and you're probably going to want maybe some sort of scripting language so people don't have to use C++ to make their game. This is where the facade pattern comes in. The use of the facade pattern allows you to hide all of your implementations behind a class and use a third-party library. For example, instead of building your own physics engine, create the API for it and then use a third-party library such as React Physics 3D under the hood. This means that at any time you can swap out the API with your own implementation or swap it out with another third-party library. The same would go for your entity list and entities using a library such as ent. What are these sort of libraries that you can use? Well, the first would be a window manager. So a window manager is something that you want to use, such as GLFW, SDL, SFL, or Win32 API. Now, the most common of these would be something like GLFW or SDL. A lot of games use SDL if they're using DirectX on the Windows platform, or you can go down the approach of using the Win32 API if you want Windows specific. Obviously, the downside being it would only work on Windows, so my recommendation would be something like GLFW or SDL. The other you want is a graphics engine. Now, the choice of your graphics engine here doesn't really matter too much as long as it's depending on the systems you want. The most common approach is to use something like OpenGL or DirectX. Vulkan and Metal are a bit more advanced, and Metal would be specific to Apple. First, diving into OpenGL, there are two versions. There is Legacy and there is Modern. Legacy is OpenGL version 1 and 2, and Modern is 3+. You'd want to use Legacy if you want the fixed pipeline, so not having to do your own shaders, and you're just writing some sort of basic physics graphics engine, sorry. The most common approach would be to use a modern sort of OpenGL version, such as 3 or 4. The reason for this is you get access to being able to create your own shaders. The other choice, which a lot of game engines use, is DirectX, and this is because it's built and supported directly by Microsoft for Windows. Limitation being it's only on Windows. DirectX has two sort of major versions at the moment, DirectX 11 and 12. DirectX 11 is more like modern OpenGL, and DirectX 12 is a bit more like Vulkan, so it's a bit more low level. Another popular choice, which is somewhere you want to start once you've got a bit more of an understanding of game engines and graphics engines specifically, is Vulkan. Now, if OpenGL is C, Vulkan is assembly. It is that sort of hard. You've got to manage your own memory yourself in Vulkan and kind of do everything yourself. It takes over 1,000 lines of C++ code to draw a triangle in Vulkan, for reference. So yeah, DirectX 12 would be more like Vulkan, having to write those 1,000 lines of codes for your triangle, and DirectX 11 is more like OpenGL 4. Then you have Metal. Metal is what DirectX is to Apple. It is specifically for the Apple ecosystem, and it's what you want to use if you're developing for iOS or Mac specifically. My recommendation here would be to start with modern OpenGL, and then if you really want to get into the depths of graphics engines, jump into something like Vulkan. The next is your physics engines. Now, there's quite a lot of open source physics engines out there and a lot of proprietary ones, but we'll focus on some of the top open source ones. The new kid on the block is Jolt Physics. This was created by one of the creators of Horizon Forbidden West and is currently being implemented in Godot, for example. This is a great physics engine to start with, however, the documentation is a bit limited. Another really popular choice is Bullet Physics. Now, Bullet Physics is kind of not supported too much these days. It's moving into the Python sort of space for robotics. However, it is still a great library if you want a physics engine. The other is React Physics 3D. This is the one I've used the most. I do enjoy it. It does have its downsides like any. And this one, again, is sort of focused on modern C++ and is widely supported and has great docs. The other choice would be something like NVIDIA PhysX, which is supported by NVIDIA. Now, out of these, I would recommend either Jolt or React Physics 3D. With any of these, it's worth noting that when you're trying to implement these into your own engine, you don't want to couple them together with other systems. And it's worth keeping in mind the approach you're taking. If you are taking a data-oriented approach, you want to make sure that you're not breaking that design pattern when implementing these. So for entity management, you probably don't want to write your own ECS. It's a lot of work. It can be as simple as just arrays and using the indexes, or you could use GUIDs or something like that. However, a much simpler approach is to wrap it in something like ent or flex. Now, if you're interested in using modern C++ features and metaprogramming using templates, then you'd want to use ent. Ent is a great library. It's used in Minecraft, for example, on the Bedrock edition, and it's widely supported and used, and the docs are fantastic. The other option would be something like Flex. Flex is a C API, so if you prefer the C-style APIs over C++, you'd want to use Flex. My choice for this would be ent, mainly because it is widely supported in industry as well, has lots of funding behind it, and is a really nice library to use. So what are some practical tips for getting started then? If it wants to press, there we go. So when getting started, you want to start small and iterate. So you want to take the agile approach here. If you don't start small and iterate, you're quickly going to be swamped down with features that you want to implement, and you're never going to get anywhere. The other one is you want a modular design. So those systems that I implemented before, for example, the Windows and Ball systems, you want those systems to not depend on each other. So you don't want tight coupling between your systems, otherwise it's just going to become spaghetti code. Another thing to watch out for is scope creep. So everyone wants to create the next best sort of engine comparing to Unreal or something like that. It's just probably not the case. You don't have every day to work on this. It's not a full-time job. You do want to just focus on small little items. Don't be afraid to leverage third-party libraries. Use React Physics 3D, use ent, and so on. You don't want to have to try implement these yourself to begin with. Make sure you read and learn. There's lots of resources online to read and learn, so constantly be reaching out and trying to find new resources to learn. The other recommendation would be diving into open source game engines. Now, for example, you might want to dive into the Godot source engine and see why the source code is messy, or how you could take inspiration from certain things. Not just Godot, but there's heaps of other engines out there. For example, Source Engine has been leaked on GitHub, so you could go and check that one out. And there's lots of other sort of open source engines as well. Most importantly, have fun. You don't want to have creating an engine be your second job. You want this to be something that you sit down on the weekend, write some code, make a cool engine, and have fun doing it. So what are some common pitfalls, and then how do we avoid them? Well, the most common pitfall is over-engineering. Everyone has been there in any sort of software development where you over-engineer your code. The other one is tight coupling between systems, like I've mentioned before. This is where all of your systems are too dependent on each other, and all of a sudden you don't have modular designs and reusable libraries. For example, I've seen code before that I've written where your physics code is directly coupled to the renderer. This means that if I wanted to change the renderer in the future, I would also have to change my physics code, and it's not good. And this is for debug purposes, so you might think, oh, I'm just going to add this in here and sprinkle this in here to help me debug my physics, and then you end up realizing that if you want to change this system, you have to change everything else. And that kind of leads me into sort of the poor architecture sort of designs there as well. And here are some resources, I guess, for learning. So the most common is Learn OpenGL, and this would be if you want to learn sort of your graphics APIs and learn how to create your own graphics engine. The other one is Game Engine Architecture by Jason Gregory. This is an amazing book on architecture itself in a game engine. and if you want to really dive into the depths of how AAA studios design their engines. The other is physically based rendering book. This is more of an advanced sort of rendering techniques, so making your scenes look as realistic as possible. This book focuses on companies from Pixar and so on that have developed in-house render engines, and it's a great book if you do want to get down that sort of path. The other one is AAA studio research papers. Now, EA, Ubisoft, and all them Epic Games are always publishing research papers online about all the new techniques they're coming up with. For example, Nanite has a research paper on their cool rendering techniques in Unreal Engine 5. So yeah, definitely check out them. And then last of all, being YouTube. YouTube is a great learning resource, as we all know, and there's lots of YouTubers out there building their own engines that you could follow along with. So before I move on to questions, I do have a very quick demo that I was going to run through, if I can get it to work. But I think we'll move to questions first, and then I'll get it loaded. So yeah, any questions?
So, hey James, I have two questions. The first one is you talked about some advantages of the entity component system.
Yep.
And is there any advantages of OOP design over entity component system? This is my first question. My second question is, you talked about there are some downside with React Physics 3D library, but you didn't say what exactly are they. Maybe you can elaborate?
Yep. So I'll start with the ECS using OOP. Is that how you would implement using OOP, or?
Sorry, yeah, my question is there any advantages of OOP over ECS?
So your ECS would still be an OOP approach, so to speak. You'd still have an entity, class, or object. However, the underlying data structures would be data-oriented. Mm-hmm. So, for example, your entity would just be a class that wraps, an int or an ID of some sort, and it would have a nice method on it called getComponent. And the data itself is stored in a data-oriented way, so it's stored in those contiguous arrays. And what was your second question?
React Physics 3D, any downside?
So not specifically, I guess, with the engine, more so implementing it. So a lot of these third-party engines, such as React Physics 3D, implement their own ECS under the hood. So they're almost mini sort of engines, so to speak. So implementing them, you often have to call into their regions of memory. So they have an ECS, but anytime you call their rigid body, it exists in RAM, so it's not actually coupled next to your rigid body in memory. So the issue for that is you might be iterating over your rigid bodies. However, because it's using a pointer to their rigid body, it's actually still having to go out into RAM, and then all of a sudden you've got a CPU cache miss. So yeah, I hope that explains it.
Yeah, thanks.
No problem.
It's helpful.
Awesome. Any other questions?
This was more around the structure of systems. So you mentioned that the input handling should be done at the same time as rendering. If your systems that do game updates, etc., depend on the input handling, are there any sort of ways you know that can easily sort of handle that, like events? What have you found that works best for that?
Yeah, so the best way to do that would be events, and I did have it but I didn't cover it, was you would essentially store the events for 2 or 3 frames after they're inputted, and this would mean that no matter what, even if you're calling game logic in the tick, you can still handle those events afterwards. So that's sort of how you do it, is you'd store those events in an array somewhere and have a read events with a generic sort of thing, and you'd store it for 2 to 3 frames. Awesome. Front.
Hey. Yeah, hey. The question I had was, are there practical reasons why you would want to implement your own game engine, or is it more just for learning?
More so for learning. These days, most sort of studios will use Godot or Unity or Unreal. But it's more so just a fun thing on the side, but it is still applicable. So if you go and work at EA and you want to do engine work, you might work on their Frostbite engine, which is the one that they use for all their games. So there is still work out there for it. So it's more like learning, and then you could get a job in it if you want. So yeah. Awesome. Any other questions? No? Yeah.
Hi, I do have one question. Is there any benefit in actually coupling some of your systems together, such as the rendering pipeline and your physics engine? I mean, yeah, you're saying that's a downside, but is there potentially any efficiencies that you could gain from that?
I guess there would be efficiencies because, you know, all of a sudden it's not having to rely on third-party sort of interfaces or anything like that. But I would still iterate that the issue is then you wouldn't have a modular design. So if I want to reuse my physics engine somewhere else down the future in a different engine or use it somewhere else entirely, all of a sudden I can't because I've got to bring my renderer with me. Obviously, again, there is upsides to it. You can sort of bypass having to do that middle layer and hide behind interfaces. But yeah, it's kind of performance versus, I guess, modularity at the end of the day. If it's just for one sort of game engine, you might want to couple it a bit, but it's still probably not the best idea. But yeah. One more.
Hi, being a very avid online gamer, my questions are with first the rendering engine. Is it possible to do selective rendering, and which engine would be best at that? So imagine the situation where you have a camera viewport that is behind a wall, and you have to render what the character avatar could see, but not what's behind or obscured by the wall. So which engine would be good at that?
All sort of modern engines do that, and even OpenGL itself, for example, implements culling, so anything that's behind the camera viewport won't get rendered. There is, obviously, you want to make it so it's not maybe running physics in the background, so Unity and Unreal both and Godot all do that.
Right. It's just I've always not noticed that most of the games don't do it. They force the camera to zoom in.
Yeah, so they'll still implement culling, so anything that's not being rendered or on the screen won't be rendered. They might still be running game update. For example, if you have a player behind you, you still want it to, or an NPC behind you, you still want it to continue walking, but you might run that at a slower sort of tick rate or something. But yeah, both Unity and Unreal implement that.
Yeah, it's just from the player perspective, the forced zoom in is annoying as hell. It's like, can't they just selectively render the wall as transparent, maintaining the viewport distance? That's what I'm trying to get at. It's just one of the quirks. The other one with physics collision detection.
Yep.
What about when someone with a backpack sits on a chair versus someone that doesn't? Why is it that all the time the backpack goes through the chair?
That would be because the backpack doesn't usually have a collision collider on it. So usually you just put a capsule collider around the player itself, and any sort of third-party things like hair don't have colliders on them. So it just makes it so it's easier to, yeah. Less physics is good because then it's not going to be running as slowly. So yeah. That's all good. Awesome, cool. Thank you for that. And yeah, thank you guys, and hope you have a lovely rest of DDD. Cool. Leave it.
Hello, how it's going? Please find your seat. Come on. Let's come to the front. There's still a little bit more space left. Welcome to the session 2 of the day of this River Room 1. We have the end of microservices, and we have Nick, or Nicholas Sia is a staff member, staff engineer at VGW with 15 years experience across different range of industry. He's going to tell us more about why this is the end of microservices. Welcome, Nick, please.
Cool, good. This is a microphone, and that's how microphones work. Good morning. Don't worry, I'm on your side. I have a love-hate relationship with microservices as well, so I'm just going to spend the next 40 minutes hating on microservices, which I assume what you came for. So, before I start with all of that, I'd like to take a moment to thank all of our very wonderful sponsors that we love very much, along with Ja and her team, the fantastic DDD staff who worked really hard to make all of this possible. This room is brought to you by Microsoft, but maybe Jez meant to say that, I'm not sure. So just before I start, I'd like to say that everything I say today is my own stinky opinion and does not represent those of my company. So as following on from Gia's kind introduction, I have worked professionally in software for about 15 years. I started very early. My umbilical cord was detached and then plugged into a random port on a computer. And it all went downhill from there. So I've worked in, mining, telecoms, VR, et cetera, and inside of those things, I really had a habit of working on all the things. So that's, that's all your infra bits, CI/CD, backend, databases, networks, blah, blah, blah. I don't do front end, so it's more like most of the things. I also don't do AI or ML, so now it's just some things. I do some things. And also, let's advise you that I'm not Jackie Chan. I'm just a friendly software developer, and I promise I am friendly. I'm going to tell you what the singular, the bestest practice is the bestest. I'm going to do that with my friend Best Practice, GPT. Oh. No, wait. Yes. It's not best practice anymore because there's some bad things about microservices. So it's not good anymore. Instead, I'm going to go look for a new best practice. Oh, wow, what a shock. I was going to say modular monolith. Oh, I haven't heard that one. Glad this is new. And serverless functions. Thank you. So, don't think it was called a monolith back then. It was just called code, like the code, the thing. Back in we were mostly a cost-centered days, and we just spent money, and who knows what we did. I don't know, there's all these nerds just over here typing, but whatever. And then we decided to make the code smaller, sort of. We split it up. I don't know, the squares got smaller, that's all I saw on the PowerPoint anyways. So, you know how that kind of went. Do some digital transformation. Our poor monolith get chopped into pieces. So, we broke off a few blocks. We had our, I don't know, what do people usually break off first? Like a payments service or a authentication service or something. Either way, that went pretty well. We had these things on the side, and it was nice. You'd have your team, and you'd kind of have this nice little thing off by the side, and it felt like it was all yours, and you're moving quickly. So why don't we just do it more, right? And go all these services. And the cool thing about teams, about people, about society is that we all love to work together. We can all support and depend on each other. The problem is it's a bit, just, for proprietary sake and all that. Maybe we just support and depend on each other just a little bit too much. And suddenly they kind of stopped doing work. I mean, they kept doing the work, but they they got really hard to change. It's not just this version. Please don't split us up. So all of that autonomy, or that speed we were getting, was, we were losing. That was kind of being eroded away at, right? And throw high latency on top of that. They're not talking face-to-face anymore. We're talking over networks. I guess that was a mistake, and we're going to go back to monoliths. This actually led to, actually before I say that, a quick sneak peek at what's inside your monolith anyway. It's kind of the same thing, just with components, right? It's the same thing, but the Y is a bit shorter. So this led to the greatest invention, I think, of the modern time, which wasn't modular monoliths, but it was actually the perpetual digital transformation machine. By doing this, we could create infinite value and infinite revenue just by continuously going back and forth. Remarkable what we're able to do when we put our minds together. And we were promised all this other stuff, right? So we were promised, it's easy to scale out. It's independently scalable, right? You can make this square big and then this square not big. We were told we'd be able to move more quickly, you'd be more autonomous, and you'd be able to make changes more safely because you weren't really, that part's kind of true, right? Your locus of change isn't as big. If you design it well, you're not affecting as many things. You're not going and change the whole world. So I don't really know too much about all this stuff. I'm going to reach out to someone who is a real expert. And I think the thing that makes me trust this person so much is that they are very wealthy. And the more money you have, the more good you are. Okay. So anyway, in 2002, Bezos sends an email to his company. All teams will henceforth expose their data and functionality through service interfaces. Teams must communicate with each other through these interfaces. There will be no other form of inter-process communication allowed. No direct linking, no direct reads of another team's data store, no shared memory model, no backdoors whatsoever. The only communication allowed is via service interface calls over the network. It doesn't matter what technology they use. All service interfaces without exception must be designed from the ground up to be externalizable. That is to say, the team must plan and design to be able to expose the interface to developers in the outside world. No exceptions. Anyone who doesn't do this will be fired. Thank you, have a nice day. I didn't add in that part, it's nice guy. So just going to zero in on a few key things I want to talk about, because if I take these out of context, it's easier for me to sort of reshape it into what I want to say. So all teams will henceforth expose their data and functionality through service interfaces. Teams must communicate with each other through these interfaces. Does anyone think that's a bad idea? The only communication allowed is via service interface calls over the network. Very good. We will solve these problems by making the wire very long. So, we had, or for some of you, you will have a beautiful love ball of services. I think the correct term is big ball of mud. I will call it love ball. And let's go into slow motion to see how that actually went down. Cool? That's not particularly strange. We can go to the servers depending on a database. And, well, just for convenience sake, we will plug another server straight into the database. And another one. Now, your database is going to start to get a bit harder to change, right? Any change you make, you need to go and check that hasn't gone and affected the other services. So that's not great. You would have seen that I've made it should be our left, from the service to the database, kind of has this thicker arrow. That was the service that actually originally owned that database. So I'm saying it has a strong dependency, more of a dependency on this database. And I'm just marking it as red to say, yeah, this is getting harder to change now. As a result, your connected service that owns that database is also going to get a fair bit harder to change. To change functionality, to add functionality, you might need to change or add some tables. And if those are being depended on by these other services directly, you're in a bit of a bind, right? You're going to have to organize some sort of downtime, or maybe you can do some clever deployment tricks to avoid that, but still, you're giving yourself more of a headache than you really need to. And just for some extra fun, yeah, these services might go, oh, we'll do the right thing. Or the service on the right will do the right thing, and I won't go straight to the database. I'll get it from this other service which hosts that functionality. Awesome. Now that service gets harder to change as well. And the service that's reaching out is now becoming a bit more fragile. It depends on the database for some of the functionality. Now depends on this new service for some of this functionality. There's changes in either of those can potentially break this, this service on the right. It's going to make it very difficult, or more difficult to make changes in that database and service. So, it continues. We add another service, and now, especially if you've got those services, we just want to add a bit of extra functionality. We don't really have the time to build a new interface for it. You do actually kind of end up in this kind of situation where, because of all these changes against the database, and we don't really have time to do a really nice automated test suite, everything starts to become very fragile. As most of you will know, when you die in systems architecture, you die in real life. Fortunately, there's Tom Cruise in Edge of Tomorrow. So when he dies, he doesn't die. So I don't know. We don't die. I just want to put the picture there. So let's do that again one more time. But I'm going to swap a service and database around. So we've got the same, it's the same thing, but I've just moved the database to the left, so I've got more right to, I'm going to go plug in all these things, right? It's so much better now, wow. So you have the same thing, right? If you're plugging a lot of, if you're plugging a lot of services into this service now instead of the database, yeah, that service is also going to become difficult to change. It doesn't get a free ride just because it's a service. I would probably contentious, but I would probably not necessarily differentiate database too much from service either, especially now that we're starting to see things like data products, where you are very intentionally exposing kind of a data contract. So, go on, more things plug in, and you kind of get the same thing. That flame was left in there, my mistake. But the key thing is, it's the service now that has multiple dependents on it. And yeah, it's difficult to change. But if that's your interface, if that's your front door, instead of your database or an internal service, that is something that's a lot easier to deal with. It's something that you've intentionally put out there. And you know that, hey, you understand the responsibility, or you have that intent when you design that interface. You're saying, yes, I know this is the front door. I know that people are going to depend on it. I'm going to design it so that I don't go and have all of these features. I make it very clear, you're allowed to ask this from me. And you'll see our database at the left is quite happy, or relatively happy. If you're looking at your service interface, you can kind of, I want to make an analogy to it being sort of you and your team being given high-level goals as opposed to be micromanaged, right? You want to have a clear flow that your service supports, rather than, you know, what can commonly happen is you go, oh, let me get this information, I'll post this over there, and I'll put this over there. It makes it difficult to change later because eventually every behavior of your system becomes part of your API. Not just the open API schema or whatever, but your bugs, even things like network reliability, latency, every observable behavior becomes part of your API, whether you want it or not. I didn't make that up, that was someone else. So, don't get any funny ideas. Don't do this. That looks cool, it looks like a sword. Yeah, that won't work here. I don't know what you'd end up with. I'd like to try it as a thought experiment, but I think there's no way. I mean, actually, some companies will kind of have something that looks like this, but they may have a very complex domain that requires a whole lot of internal services. That won't be true for most of us, or just by having a really long, I don't know, pipe. Cool. So actually, I think we're getting better at this, and a lot of us kind of get here and like, okay, we're going all right. That's kind of your month one, if you're lucky. As you start to grow out your system, as time moves on, it gets harder and harder to maintain a clear boundary. And I think that a lot of tooling came out, promising to, you know, we'll make it go faster, or if you use this, you know, you'll do microservices the goodest. But I think the problem lies elsewhere. So this is still, my advisor told me this is still culturally relevant. You basically have to fend off these guys, and I think for anyone who's spent some time in software engineering, we've all been this thing. So, you know, wandering around, just hanging out in our office, or remote. Oh, don't do that, please. Okay, that doesn't go there, but okay, fine. And it looks silly, but I think that anyone who's, you know, worked in a sizable team for a while would have experienced this, right? Like, come on, you know, help me out here. I've got a deadline. just one endpoint, brah. And that's kind of where it starts, right? So now it gets hard to change your database, and once you've not really, once that happens, it gets easier. Oh, you know, I've already got a connection. Can we just add this on and that on? And big ball of mud is the ending. And we talked a bit about, you know, we can use queues or, I don't know, like two cups on a string. It doesn't matter. I think a lot of those things, while helpful for physical decoupling of services, helped a bit reliability, but I don't actually think there's any tool that can really stop this from happening. Your best shot, unfortunately, or fortunately actually, is yourself. So what my opinion is that no matter what controls you put in place, so you can have your you know, repository controls or your code owners, or you know, maybe change approval boards or whatever, it doesn't really matter. What matters at the end of the day is someone who has a vested interest in maintaining sort of the city borders, right? So you need to maintain the structure and the architecture of kind of your boundary, you know, of your systems. In a very literal sense, you'd very much, I think, the responsibility is on you to actually fight for your team's freedom. And sometimes that means, you know, feeling like the bad person and saying no. But that is what needs to be done, right? And I'm deadly serious when I say I don't think it's too different to setting borders, setting boundaries in the relationships you might have in real life with your friends and family and whoever. So I've got the custodian now. Go on, get out of here. So looking back, I think what would have made my life easier is if I was a better custodian than I was, and if I didn't try to be the sus guy so much. It's difficult. You know, in the general case, you probably feel like you probably like your team and you don't want to say no and you want to help them out. They might be having a tough deadline. Maybe they've misplanned, maybe they haven't, but you've got an opportunity to just, make that extra endpoint and get them what they need. And more often than being a custodian, I was that sus guy, right? I was desperate to get something over the line, and I would, what do? You message, you message the tech lead, or you message one of the developers, say, oh, just prove this, trust me, it's fine. So I think one crucial thing is try to be more of the custodian and less of the sus person. There's business reality at play. Sometimes things need to go over the line. But I think the biggest thing missing from some modern teams is the lack of a custodian around that boundary. And if you don't define that boundary properly, and it's too broad, the custodian's looking over too much stuff, you're actually still going to get a lot of coupling within the internal services because they don't really have too much of an interest in they're focused on defend their boundary, not so much what's within it. Okay. Rich man. Repeating myself, all teams will henceforth expose their data and functionality through service interfaces. Teams must communicate with each other through these interfaces. I personally think this makes a lot of sense. There was one bit I cut out before that he said. All service interfaces, without exception, must be designed from the ground up to be externalizable. That is to say, the team must plan a design to be able to expose the interface to developers in the outside world. No exceptions. I think this is crucial. You will have your mindset will differ. If you're thinking about something as an internal service, you're going to think of it from the angle of, what can it do for me? You're going to give it very rich functionality. You might have it expose lower level functionality, right? So you might have it work with smaller level primitives rather than just providing a very generic front door. Don't know if this is a good idea. For example, you might just have it exposing, CRUD endpoints directly to your data model if you wanted to. I mean, that's basically what a database is, right? But you'll think very differently when you're looking at a service you intentionally meant to build as an external service. You know you're going to have to support it. You know it's going to take sort of very very varied requests, varied workloads. And when you think of it that way, I think you'll design it very differently. This is the front door. The strangers are going to come knocking. I'm just going to have this very clear interface, very intentional interface, supporting with the audience in mind. Whereas when you have an internal interface, I think you can be a bit more vague and be like, oh, I'd like to support this feature functionality. I think that's okay. So that's kind of a very simple visual version. You've got that internal service which is protected by an external service, and you'll be able to plug more things to that internal service because there are less external dependencies on it. When the dependency inside your team, you get a lot more freedom there, of course. And I can't stress this enough. Defend your autonomy. So, the one thing I was originally going to take issue with was this line, might be a bit hard to see up there. It says, the only communication allowed is via service interface calls over the network. I didn't like how how he specified a physical, I guess, the transport here. I think it's less that it's less that we want to specifically say they have to communicate over a network, and more that I think the benefit of that was more like just communicate over a single protocol. Saying that we just want to have these services connected over a network, over networks, was I think it was really damaging. I think that had a really big cost. That was quite unnecessary. And I explained why. So it's kind of like this is a one I wasn't sure if I wanted to put in. Basically, the analogy I want to make, what I want to say later is, you start to see very common patterns. This is, for example, which is very simple, layered, a layered application architecture. The importance is actually more on the data models and the relationships than these physical things, right? Whether it's talking over a network, or it's a service, or it's a database, or it's not a service at all, it's actually your domain code or your web routes or something. They all have relationships, and they all work with data. That's what matters more. I won't give away too much just yet. So, moving on, we were given a lot of promises about microservices, right? If you do a stinky monolith deployment, you would, you'd start deploying, and you'd crash, and yes, everything would go down. And that was one of the key selling points of microservices, right? So if you have a failed monolith deployment, you would lose all your functionality. You're fully down. Okay, so let's say we do independent deployments, and that fails. That's okay. It's only that single service that's gone down, right? So you've got all the interconnected services, and while, yeah, they might not actually crash because they are, I guess, physically isolated, you still have the dependencies, and even if you're able to degrade your functionality to sort of cut off that dependency on whatever's failed, you've still lost that functionality. That's not only like, wow, this is the best, this is absolutely fine. We just lost some functionality, that's all. We didn't get a crash. Great. Extra fun with microservices, we go back to deploying, and everything's fine. And then your other services still catch fire. So yeah, adding an extra issue here. I think one thing I want to drill in on with this is that microservices came with, Bezos said his piece, and we had service-oriented architecture at the time. With microservices, like everything else, it came and there were good intentions, and there was a problem it was solving. And then it kind of turned into, as every technology does, a bit of a cult, right? Now there's rules. You need to do the holy things to do microservices right. You need to make sure all your services are independently deployable. I'm not going to actually, I think the way microservices was done created some of these problems, but I'm not going to blame it on the idea of microservices. And one of the key things I want you to take away from this talk is not to think about, these are microservice deployments, these are not microservice deployments. No, think about, if we thought of microservices as, these, don't share your data store, deploy independently, have a team that owns it. Those are actually the things that matter, and those are the sort of the knobs you can turn to suit what you're actually trying to do, right? To actually meet the needs of the team. If you find it easier to just deploy all at once, with your microservices, go and do that. You can do that by spinning up a full new environment and then doing a full cutover. It's a bit expensive, but you can do that. And there's benefits doing so. You now only manage a single version of your system instead of, and I forget the formula, but you know, if you have 5 microservices all connected to each other and each can have n number of versions, that's a lot of different states your system can be in. It's much harder to reason about. You can mitigate it with things like contract testing and so on, but you're still making a headache for yourself, I think. So, I think, I don't know where this one's at. I think I've done probably over 100 interviews in my career, and I think one that comes up a lot is, well, one question I like to ask a lot is, you know, why do microservices? One that comes up a lot is, you know, scalability or performance. Performance is a bit odd, right? Because all you've done with microservices is make the wire a lot longer, right? You now have network latency to deal with instead of, you know, just change the instruction pointer, you know, an internal call is going to be on the order of microseconds or nanoseconds, as opposed to those very slow network calls, right? But on the other hand, if you say scalability, there was a little bit of mix-up here. Some people think that monolith means, you know, you just have a single box and you can't horizontally scale that. Some people think it just means, you know, you have a single big application. So I think there was a mix-up there, and that's why some people said, you know, it's easy to scale. I think one of the key points is probably independent scalability. So, okay, you can scale this one up, you can scale this one up, you can have them be different sizes. And you know, we won't be contending on a single piece of hardware, right? So it's funny, we have all these microservices, they're all independently scalable, and they're all containerized, and then they're actually, they all ended up on the same, on shared compute hardware anyway. Of course, I'm being a little bit facetious. That became a lot easier with you know, advancements in containerization and the associated tooling, right? With the C groups now, that stuff is very easy to manage. You can control, all your containerized processes are just, you know, given a slice of time and some memory, and they're fairly well isolated. So I think I've delivered on my promise. I just did about, you know, 30 minutes of hating on microservices. I don't know if that leads us anywhere. Why did we bother with all of this anyway? Were the people who pushed for it just silly? Was it all just a waste of time? The intent was good, right? At that time, I think a lot of us would remember you had these big legacy systems. And again, you might have had that big change of approval board. It was hard to change things. You know, you had to go through so many layers of review. Similar with the database, you had to go through the DBAs. So wouldn't it be nice if we could just, you know, have our own little team, our own little village off on the side where we could do things the way we wanted to? And maybe we'll have a road going back to the capital so we can get what we need, but otherwise we have a lot of autonomy here. It was nice, and it actually made sense, right? The teams were doing this successfully. The teams were splitting off and building out their own villages on the side. They were able to deploy much faster and get results. There was definitely value out of it. The reason I say the networking, what Jeff said before about only communicating in networks, why I take issue with that is that little difference in language, it's really highly contextual, I think. I'm using this to say, hey, you know, when we were doing things in process, it was all very fast. I'm on the same machine, very quick. And we went to something much slower. which was one part of it. One cool thing I think is, one thing that was important with switching to communicating with networks was, of course, that we could now do, that was the only real way to do geo-redundancy. So now, obviously, we have, you know, Amazon with AWS with their availability zones. You can have a degree of, you know, geo-redundancy. You can even do cross-region, right? Of course, you have the cost of latency, but that was valuable. And I think quite contentiously, one that comes up is, often I hear, is the loss of transactionality, saying that you can't, well, you know, you have one service, you want to save to the database, you want to save to the you want another service to accept that, but you want it to happen atomically. You want them both to happen or not to happen. There's patterns around that. We develop patterns around that. You could save an outbox table, right, to your database, where you have a table where you just have all these. You save those events first, and then you make sure that you can just have a process read off that and make sure that definitely gets sent to that remote service. More commonly now, you end up with two-phase coordination, which for those who don't know is kind of like it can be anything. So it's a thing that sits on the side and goes, you service, you database, get ready to store this data, and here's the data. And if the database is like, okay, and the server's like, okay, we can move on. But it was rather fragile at the time. You know, you had that, now you have a new single point of failure, right? You've kind of killed off all that extra redundancy you get. But things move on. Technology got better, tooling got better. A very common pattern we see now is basically a replicated state machine driving that two-phase coordinator. So a bit technical, sorry, but where we had that single point of failure before, yes, we still have that single node that has to do everything. That's how two-phase coordination works. But it's now backed up by replicas, right? If you've used something like Amazon Aurora, where you've got a bunch of read replicas, you know that the master fails, you can have a secondary node take over. We actually applied that to two-phase coordination. So now we can kind of do, transactions across network-connected nodes. Fantastic. Yes, it's more expensive, it's slower, but you see this pattern everywhere now. DynamoDB does this, Kubernetes does this. We couldn't do that before, so I think that's where a lot of this, we can't do that transactionally. I can't make these calls to these two network-connected things in a single. I can't make these atomic. I like drawing parallels to other things in technology. You can't really, by default, write to a single file atomically. That's probably unfair to say. For example, if you're writing multiple blocks, some disks may not be able to write that atomically. You're going to have, and many file systems do, have these journaled logs that do pretty much two-phase commit, or at least crash recovery. If I wrote the first block and the computer turned off, I need to be able to go, oh, that didn't quite finish. I'm not going to make that file visible. So I think if I can take a tip out of this is to say, if you do actually see all of these same patterns. Logs are everywhere, right? Your file system, nowadays in these distributed systems, it can help you kind of see past all this. There's so much marketing marketing technology mumbo jumbo. If you actually look at those old stable patterns, logs, interfaces, it helped me gain a lot of clarity. So, I promised I'd say a bit about where we're going from here, but Sanjay's done it, taken one path forward and had a bit of a think about it. So for those of you who don't know, as far as I know, he is one of 2 senior fellows at Google. the other being Jeff Dean. He's worked on some small indie projects like TensorFlow, Spanner, and Protobuf. And I just picked 3 random ones. He's put out a lot of very impressive stuff. He released a paper, I think it was maybe a few years ago, towards the modern development of cloud applications. So him and his team did some research into, let's take stock and think about what we're going to do microservices. Not the clearest diagram. I snipping tooled this one directly from the paper. The key thing with this is, today, we still go, okay, I'm going to make a REST call or a gRPC call or a proprietary, use a proprietary protocol or whatever. Our software is still aware of this. Whereas I think logically, there was no need for that. All I wanted to say was, I have this, I want to make a call to this other service. And I want to have the data I require for, I want the request to have the right shape, but I don't care whether it's by, REST or carrier pigeon or, I don't know, letter in a bottle. Or you have latency concerns around that, but you cared more about the interface. So Sanjay's idea was to push all of that down one level. Now you have these servers which say, I want to talk to this service and I want to make these requests. And you would actually have an orchestrator one level down, which would go and go, okay, well, you said you don't want, these are relatively latency and reliability tolerant. I'm going to go chuck them on some low-cost networks. Or these ones, these are really latency sensitive. I'm going to put these together on the same rack or in the same machine. But as a developer, all you'd be doing is going, okay, I want this to connect to this, and here's some attributes I might want to have. The really interesting thing about this is when cloud technology improves, and it does always improve, let's say, we have edge networks now. Let's say there was edgier, I don't know, gooder thing. You wouldn't actually need to change your application like you do now. You would update your runtime, and it would go, oh, actually, there's these new devices that are better suited for your application. Put these over here. Oh, and lower cost ones, and put them over here. The key thing here was, I think there was a lot of, we conflated the physical and the logical. We only want to talk between interfaces, but we ended up getting all that, basically formed a sort of like a meta coupling, right? We coupled our logical stuff to the physical stuff. So, if you want to make it not talk a network and bring it back into a monolith again, you're going to have to get rid of all of the, you're going to have to change your application. I'm running out of time. A lot of these things were really context. A lot of the decisions, when you look at the past and you don't have the context, can look pretty silly. You look at the context and decisions tend to be very contextual. That's why decision records are very valuable. At the time, they had much worse deployment tooling, so deploying was a bit more risky. Nowadays, we have things like, let me put it this way. We used to have a guy with a towel. Now we have a steering wheel. We've really moved on. We can do canary deployments now, so you can kind of pop up that doesn't work, and majority of customers aren't affected. You're not going to fix this with Half-Life. You're not going to fix this with Rust. So stop thinking about best practices. Key points, really consider the boundary between logical and physical. Really consider the difference between an internal interface and external interface. Internal ones for your own team, external ones for unknown people who might depend on it later. And really think about, really focus on thinking about the audience of who's going to depend on it and who, not what. We focus too much on how big should a microservice be and what should my microservice contain. It's not about what the microservice is, it's about what you're using it for. The easiest shortcut, just think about the team that you want to support this. The the team that you want to run it, the people, and who's going to be consuming it. It could be the customer, it could be internal customers, but who's going to use it? What am I using it for? Do not get stuck on trying to identify things. That's our natural instinct. This is a blast service, or this is a blast service. This Finnish guy, I'm kind of repurposing what he said, but it's actually very similar. The key thing is focus on the data models and the relationships between them. The code is just, it's busy work. Focus on the data and the relationships. Thank you.
Cool, we won't have time for questions, but you can head over to lunch or you can stay and talk to Nick. Thank you.
Not sure if you've heard, but at Bank West, we're on a mission to become Australia's favourite digital bank and to make banking seriously uncomplicated. Imagine digital banking so simple, it makes sense to everyone, no matter who they are or where they are.
That means me.
We know that uncomplicated doesn't just happen, it's made. Not by a company or one individual or even a bot. It's made through our curiosity, honesty, and desire for change.
In other words, it's made by us.
We know becoming the favourite isn't easy, but when you're making a difference for customers, colleagues, and the community, when you feel like you're learning and growing and your ambition is matched, well then, it's all worth it.
The truth is, Australians deserve easy, useful banking experiences. This mightn't sound like a big thing, but for us, it's everything.
It would take all of us working together
to make something we're all proud of.
And that's why we need brilliant people like you.
Bank West, made by us.
MakerX is an award-winning research and development studio, building digital products and high-growth ventures at the frontier of technology. Our team of 40 experts, including 10 former CXOs, brings a wealth of industry insight and advanced expertise, including AI, Web3, and venture building. Combining an extensive library of robust technology building blocks, an entrepreneurial culture, and a proprietary R&D framework, we create groundbreaking products, open new markets for corporations, and optimize existing businesses. For those brave enough to do what's never been done, get in touch to discuss how MakerX can drive your business forward. For inventors passionate about fearless exploration and bold experimentation, MakerX offers a vibrant, inclusive environment where innovation and continuous learning are core principles. Here at MakerX, you'll work on transformative projects ranging from virtual machine compilers to non-profit mental health apps. Join us to help invent the future and make a meaningful impact in the digital world. MakerX, made for tomorrow.
Hi, I'm Melissa Herrera from DataStax, a company focused on helping developers turn their dreams into wild new realities through generative AI. We are here to make it 100 times easier and faster for developers to build Gen AI and RAG, or Retrieval Augmented Generation, apps and experiences that you can quickly get into production. DataStax offers a one-stop Gen AI stack and data API that gives developers all the data to build a complete RAG app for a faster and easier path to production. We've also added Langflow, making it easy for developers to build one-click RAG at scale, with an open-source visual RAG framework with drag-and-drop data flows and pre-built components for connecting to any API, data source, or database. One-click deployment, and seamless integration with AstroDB for more relevant answers with ultra-low latency, giving you 20% higher relevance, 9 times more throughput, and 74 times faster response time at 80% better TCO. DataStax delivers a RAG-first developer experience with first-in-class integrations with leading AI ecosystem partners. So we just work with developers' existing stacks of choice.
Why is Mandel Group such a great place to be? Gee, that's hard. Where do you start?
Immediately what comes to mind is the people. Might sound like a cliche thing to say, but genuinely I believe that we've got the best people, not only technically and from a consulting perspective, but just generally as people.
Mantle Group principle that resonates most with me. I smile because there's a few, look, they actually all resonate with me, but I would say in it together.
Love what you do and be awesome at it. In my mind, people are at their most productive and engaged and enjoy their work the most when they're doing something that they're passionate about.
The Mantle Group principle that resonates most for me is make good choices. It's the fundamental one that sits almost underneath the other principles and allows us to use those principles to make our decisions and how we work.
Make good choices. I love this one because it's around treating people as an individual and trusting them to make a choice that's right for them.
We're close to 1,000 people now, and we still are able to be principle-based where our team genuinely make good decisions and use their principles to guide themselves.
Mantle Group principles enable me to be more me at work.
We're breaking the mould and ensuring that we create an experience for people that is unique to them and really redefines what work means for people.
The world is changing fast. In the new world of business, the fast and the agile will thrive, while the slow and the inflexible will be left behind. To compete, you know that digital transformation is a must. You must leverage the cloud. You must turn to methodologies like DevOps. You must innovate software at blazing fast speed. It's a lot of musts. Thankfully, there's Tricentis. We accelerate digital transformation with the most comprehensive continuous testing platform. From the best in-class test automation and test data management to industry-leading performance testing, system simulation, and risk-based testing. With the power of AI, you can rapidly design, automate, and orchestrate virtually any type of test for your business to accelerate software delivery. Built for enterprise scale, it increases speed, reduces costs, and decreases risk. So you can release software faster, fund new growth initiatives, and be even more confident in your success. And when that happens, you bring new products to the market faster, speed innovation, and create more fiercely loyal customers than you ever imagined. It's no wonder that companies like McKesson, Dell, and Mercedes-Benz turn to Tricentis to accelerate their digital transformation. Tricentis. Speed changes everything.
Go.
It's always about the people. Yeah, it's always about the people you work with.
I see the company's commitment to its employees, the commitment to the community, and that feel there's a ton of opportunity for support and empowerment here.
It makes me really proud to say that I work for Woodside. I can see the contributions that they make to our community, right from the nippers all the way through to the community associations.
You have that accessibility to leadership, and I feel as if my view and my contributions are valid.
It's the fact that it's a very reliable company, and our customers value that reliability. They value energy security. They need it.
There's so many conveniences and comforts that we enjoy today that we expect to be there tomorrow. Whether it's preparing a meal, charging your mobile phone, Woodside's ability to provide reliable forms of energy really allows us to help people access a better quality of life.
We play quite an important part in everyone's life, and that's quite special. And I'm quite proud that I get the chance to work for a gas plant like this.
Not sure if you've heard, but at Bank West, we're on a mission to become Australia's favourite digital bank and to make banking seriously uncomplicated. Imagine digital banking so simple, it makes sense to everyone, no matter who they are or where they are.
That means me.
We know that uncomplicated doesn't just happen, it's made. Not by a company or one individual or even a bot. It's made through our curiosity, honesty, and desire for change.
In other words, it's made by us.
We know becoming the favourite isn't easy, but when you're making a difference for customers, colleagues, and the community, when you feel like you're learning and growing and your ambition is matched, well then, it's all worth it.
The truth is, Australians deserve easy, useful banking experiences. This mightn't sound like a big thing, but for us, it's everything.
It would take all of us working together
to make something we're all proud of.
And that's why we need brilliant people like you.
Bank West, made by us.
MakerX is an award-winning research and development studio, building digital products and high-growth ventures at the frontier of technology. Our team of 40 experts, including 10 former CXOs, brings a wealth of industry insight and advanced expertise, including AI, Web3, and venture building. Combining an extensive library of robust technology building blocks, an entrepreneurial culture, and a proprietary R&D framework, we create groundbreaking products, open new markets for corporations, and optimize existing businesses. For those brave enough to do what's never been done, get in touch to discuss how MakerX can drive your business forward. For inventors passionate about fearless exploration and bold experimentation, MakerX offers a vibrant, inclusive environment where innovation and continuous learning are core principles. Here at MakerX, you'll work on transformative projects ranging from virtual machine compilers to non-profit mental health apps. Join us to help invent the future and make a meaningful impact in the digital world. MakerX, made for tomorrow.
Hi, I'm Melissa Herrera from DataStax, a company focused on helping developers turn their dreams into wild new realities through generative AI. We are here to make it 100 times easier and faster for developers to build GenAI and RAG, or Retrieval Augmented Generation, apps and experiences that you can quickly get into production. DataStax offers a one-stop GenAI stack and data API that gives developers all the data to build a complete RAG app for a faster and easier path to production. We've also added Langflow, making it easy for developers to build one-click RAG at scale, with an open-source visual RAG framework with drag-and-drop data flows and pre-built components for connecting to any API, data source, or database, one-click deployment, and seamless integration with AstraDB for more relevant answers with ultra-low latency, giving you 20% higher relevance, 9 times more throughput, and 74 times faster response time at 80% better TCO. DataStax delivers a RAG-first developer experience with first-in-class integrations with leading AI ecosystem partners. So we just work with developers' existing stacks of choice.
Why is Mandel Group such a great place to be? Gee, that's hard. Where do you start?
Immediately what comes to mind is the people. Might sound like a cliche thing to say, but genuinely I believe that we've got the best people, not only technically and from a consulting perspective, but just generally as people.
Mantle Group principle that resonates most with me. I smile because there's a few. Look, they actually all resonate with me, but I would say in it together.
Love what you do and be awesome at it. In my mind, people are at their most productive and engaged and enjoy their work the most when they're doing something that they're passionate about.
The Mantle Group principle that resonates most for me is make good choices. It's the fundamental one that sits almost underneath the other principles and allows us to use those principles to make our decisions and how we work.
Make good choices. I love this one because it's around treating people as an individual and trusting them to make a choice that's right for them.
We're close to 1,000 people now, and we still are able to be principle-based where our team genuinely make good decisions and use their principles to guide themselves.
Mantle Group principles enable me to be more me at work.
We're breaking the mould and ensuring that we create an experience for people that is unique to them and really redefines what work means for people.
The world is changing fast. In the new world of business, the fast and the agile will thrive, while the slow and the inflexible will be left behind. To compete, you know that digital transformation is a must. You must leverage the cloud. You must turn to methodologies like DevOps. You must innovate software at blazing fast speed. It's a lot of musts. Thankfully, there's Tricentis. We accelerate digital transformation with the most comprehensive continuous testing platform. From the best in-class test automation and test data management to industry-leading performance testing, system simulation, and risk-based testing. With the power of AI, you can rapidly design, automate, and orchestrate virtually any type of test for your business to accelerate software delivery. Built for enterprise scale, it increases speed, reduces costs, and decreases risk. So you can release software faster, fund new growth initiatives, and be even more confident in your success. And when that happens, you bring new products to the market faster, speed innovation, and create more fiercely loyal customers than you ever imagined. It's no wonder that companies like McKesson, Dell, and Mercedes-Benz turn to Tricentis to accelerate their digital transformation. Tricentis. Speed changes everything.
Go.
It's always about the people. Yeah, it's always about the people you work with.
I see the company's commitment to its employees, the commitment to the community, and that feel there's a ton of opportunity for support and empowerment here.
It makes me really proud to say that I work for Woodside. I can see the contributions that they make to our community, right from the nippers all the way through to the community associations.
You have that accessibility to leadership, and I feel as if my view and my contributions are valid.
It's the fact that it's a very reliable company, and our customers value that reliability. They value energy security. They need it.
There's so many conveniences and comforts that we enjoy today that we expect to be there tomorrow. Whether it's preparing a meal, charging your mobile phone, Woodside's ability to provide reliable forms of energy really allows us to help people access a better quality of life.
We play quite an important part in everyone's life, and that's quite special. And I'm quite proud that I get the chance to work for a gas plant like this.
Not sure if you've heard, but at Bank West, we're on a mission to become Australia's favourite digital bank and to make banking seriously uncomplicated. Imagine digital banking so simple, it makes sense to everyone, no matter who they are or where they are.
That means me.
We know that uncomplicated doesn't just happen, it's made. Not by a company or one individual or even a bot. It's made through our curiosity, honesty, and desire for change.
In other words, it's made by us.
We know becoming the favourite isn't easy, but when you're making a difference for customers, colleagues, and the community, When you feel like you're learning and growing and your ambition is matched, well then, it's all worth it.
The truth is, Australians deserve easy, useful banking experiences. This mightn't sound like a big thing, but for us, it's everything.
It would take all of us working together
to make something we're all proud of.
And that's why we need brilliant people like you.
Bankwest, made by us.
MakerX is an award-winning research and development studio, building digital products and high-growth ventures at the frontier of technology. Our team of 40 experts, including 10 former CXOs, brings a wealth of industry insight and advanced expertise, including AI, Web3, and venture building. Combining an extensive library of robust technology building blocks, an entrepreneurial culture, and a proprietary R&D framework, we create groundbreaking products, open new markets for corporations, and optimize existing businesses. For those brave enough to do what's never been done, get in touch to discuss how MakerX can drive your business forward. For inventors passionate about fearless exploration and bold experimentation, MakerX offers a vibrant, inclusive environment where innovation and continuous learning are core principles. Here at MakerX, you'll work on transformative projects ranging from virtual machine compilers to nonprofit mental health apps. Join us to help invent the future and make a meaningful impact in the digital world. MakerX, made for tomorrow.
Hi, I'm Melissa Herrera from DataStax, a company focused on helping developers turn their dreams into wild new realities through generative AI. We are here to make it 100 times easier and faster for developers to build GenAI and RAG, or Retrieval Augmented Generation, apps and experiences that you can quickly get into production. DataStax offers a one-stop GenAI stack and data API that gives developers all the data to build a complete RAG app for a faster and easier path to production. We've also added Langflow, making it easy for developers to build one-click RAG at scale, with an open-source visual RAG framework with drag-and-drop data flows and pre-built components for connecting to any API, data source, or database, one-click deployment, and seamless integration with AstraDB for more relevant answers with ultra-low latency, giving you 20% higher relevance, 9 times more throughput, and 74 times faster response time at 80% better TCO. DataStax delivers a RAG-first developer experience with first-in-class integrations with leading AI ecosystem partners. So we just work with developers' existing stacks of choice.
Why is Mandel Group such a great place to be? Gee, that's hard. Where do you start?
Immediately what comes to mind is the people. Might sound like a cliche thing to say, but genuinely I believe that we've got the best people, not only technically and from a consulting perspective, but just generally as people.
Mantle Group principle that resonates most with me. I smile because there's a few. Look, they actually all resonate with me, but I would say in it together.
love what you do and be awesome at it. In my mind, people are at their most productive and engaged and enjoy their work the most when they're doing something that they're passionate about.
The Mantle Group principle that resonates most for me is make good choices. It's the fundamental one that sits almost underneath the other principles and allows us to use those principles to make our decisions and how we work.
Make good choices. I love this one because it's around treating people as an individual and trusting them to make a choice that's right for them.
We're close to 1,000 people now, and we still are able to be principle-based where our team genuinely make good decisions and use their principles to guide themselves.
Mantle Group principles enable me to be more me at work.
We're breaking the mould and ensuring that we create an experience for people that is unique to them and really redefines what work means for people.
with us. She's a senior software engineer at Bankwest and have just won Witwa Award last week. Congratulations. So she's actually going to talk about GraphQL. I don't know what it is, and now I'm too afraid to ask. It's like she read my mind, and everybody's here. Anyways, please welcome Rebecca.
Hello. We doing okay after lunch? Yeah. Excellent. So, as Joe said, my name is Rebecca and I'm here to talk to you about GraphQL. Before we get started, we're doing a quick shout out to the sponsors because obviously without their input we would not be here today. In particular, I would like to give a shout out to Microsoft, who are the sponsor for this room in particular. Go Microsoft. Now, if you have any questions, completely fine, but please leave them till the end of the presentation. And we will have a time for Q&A, and also there are notes available online. So feel free to scan the QR code now, or I will put it back up again at the end of the presentation. It's completely your choice. Too late. Now then. My name is Rebecca, like we said, and there are only two things that you need to know about me. One is I do have an intermittent hand tremor. So if you see my hand shaking, it's okay, I'm fine. This is just what they do. All it means is that all of my drinks are shaken, not stirred. The other thing that you need to know is that until recently, I didn't really know what GraphQL was, because if you work in the industry for a while, there's just so many buzzwords and so many new technologies that are emerging all of the time that trying to keep up and keep on top of everything is just not logical and not possible. And all of these technologies, they keep getting really, really hyped. In fact, they get so hyped that you can actually chart it on a hype cycle. So this is by IBM, and it is the hype cycle of emerging technologies. And if you haven't seen this before, very quick run through. We start with the innovation trigger, which is when the new technology is released to the public, is announced to the world. And everyone starts getting really, really excited about it, and it starts getting used more and more and more until we finally hit the peak of inflated expectations. Because this new technology is going to solve every problem ever. And we are going to put it in absolutely everything, and everything will be perfect forever, and we'll never have to do anything again because of this one technology that has saved all our lives. Unfortunately, we very rapidly hit the trough of disillusionment after this, because after a while it becomes apparent that maybe this one singular technology didn't actually fix everything. And maybe it's not appropriate for every scenario and use case. So a lot of people lose a lot of heart at this point, a lot of people will stop using the technology, and things are looking pretty bleak. But then, we hit a slope of enlightenment. Now this is where people pick up the technology again and start exploring and start playing with it again. But this time they're doing it with slightly more realistic expectations. So they know what it can and can't do, and they start figuring out how to use it appropriately. And then from there, after a while, we hit the plateau of productivity. And this is the goal. Because what this means is that your emergent technology has now found its place in the overall technology landscape. It's being used for the scenarios that it was actually designed for in the first place, and everybody wins. Now, the reason I'm talking through all of that is because right now, I think that GraphQL is about here. So we've been through the highs, we've been through the lows, and now we're starting to pick it back up again and starting to use it where it's appropriate to use it. Which is why, if you are someone like myself who kind of missed it the first time around and didn't really pay much attention, it would be a brilliant time to do a refresher and find out what on earth this GraphQL thing is. Which is why we have this talk today. So I'll be going through why this technology is created and what problems it solved. We're going to go through how it works and how it solves that problem. And then we'll go through the basics of getting started with both consuming and creating your own GraphQL APIs. Sound okay? Excellent, I'm seeing a lot of nods. In that case, let's go to figure out why on earth this was created in the first place. Now, I would like you to cast your minds back, all the way back to the distant past of 2012. At the time, there was this social media company, might have heard of them, and Facebook really knew how to build a website. What they didn't know quite as well was how to build an app. So at the time, their app was essentially just an adaptation of the site. And they found it wasn't performing as well compared to competitors' natively built apps. Things weren't looking too great. So they decide they're going to rebuild, and they're going to go native this time. And they've got a lot of existing architecture already, because like the majority of people, they have a lot of REST APIs that they can use and harness for this. And there's nothing wrong with REST. REST is perfect. REST is fine for a lot of scenarios. It is incredibly useful. There's a reason it's so popular. It's great for when you're working with simple data or you're working with static data. Like if you need an API that can retrieve a list of capitals and countries, then it is great for you because that doesn't change quite nearly as often as other data. It also has individual endpoints for all of the available resources, which is brilliant from a separation of concerns point of view. And it can also have stateless operations if you're building something like an API that retrieves the current weather data. By having the self-contained requests, it means that it's very easy to scale out, and it also simplifies your integration with your back-end architecture. And it's also pretty good at linking in with old systems. So on the off chance that you're working with legacy tech, it works really nicely with it. Now, it is great, but it does have its flaws and its own weaknesses. And to go through this, I want you to think about specifically the Facebook example. Imagine that you were building the news feed, and we wanted to do it using REST APIs. So we might have calls for retrieving the list of friends of the logged in user, and then we might have some calls for retrieving the latest statuses of the friends of the logged in user, and then we might have some calls for the comments that are linked to the statuses that are linked to the friends of the logged in user, and then we might have more calls for the replies and the likes of the comments of the statuses of the friends of the logged in user. And pretty quickly you see that we're dealing with a quite complex data scenario. And if you're doing it with REST and all of those calls, you're dealing with an overfetching issue because you're having to retrieve so much additional data, like the full list of friends, just to get the other parts of the information that you do need. And you're sending all of this additional data unnecessarily, which, you know, a bit of a risk. So you really shouldn't be retrieving data unless you plan to use it. You're also, kind of annoyingly, dealing with an underfetching issue because you can't retrieve the information that you need within a single or within a few API calls. You're having to do call after call after call, and that is a lot of traffic. And you have to remember, we're still in 2012 at this point. So your phones at the time are the iPhone 5 and the Samsung Galaxy S3, and they've only got 1 gig of RAM. So you really, really need to think about your efficiency. Also, all of those endpoints from before that were brilliant for separation of concerns, they require a lot of work. You're constantly having to create new ones for different scenarios or update existing ones and having to maintain all of the previous versions so you don't interrupt an existing client that's already pulling it out. It's just, I mean, it works, but it is a lot of work and it's fairly inefficient for what we're trying to do here. So Facebook thought about this for a while and created GraphQL. Now, the way that GraphQL solves this problem is that it models all of the data into a graph-like structure. So all of the nodes in the graph are various data objects, data points. So they're things like a node could be a user, or it could be a status, or it could be a comment. They're more the things of your data. And then between these nodes, the edges, we have our relationships. And these demonstrate the relationships between each of those pieces of data. So you could have a relationship that is two users being friends, a particular user being the author of a particular status. We can link everything together that way. And because it's all linked, we can traverse across the graph nice and easy. And what that means is you don't have to have a million endpoints anymore. Instead, you can have queries. So you have a single endpoint or a minimal amount of endpoints, depending on how you're building this, and you can just query for exactly the information that you want when you need it. Now this really, really helps with solving the overfetching problem, because now we're no longer sending all of this additional data across and having the risk of having to look after that when we didn't need to, and it is much more efficient. Because you can also have all of this data that we need and get exactly what you want when you want within just 1 or 2 requests. And what that means is it is so much better from an efficiency point of view, which is really good if you want to build something that's a bit more real time, like your live dashboard. It can also handle the evolving requirements fairly easily, because if you need to be able to include a new field or a new variable within it, you can just go ahead and pop it in, and it would have no impact on the existing queries that are already being used, because if they want to use it, they can just adapt their query to do so, but if they don't need it for their scenario, then they just continue on like nothing happened. So it's way easier to handle the maintenance side as well. And also, I quite like how it does error handling. So depending on how you build your GraphQL schema, you can have it so that when it errors and when it gives you your HTTP status code, you can also have it send the partial data that you've created so far and have that as part of your diagnostics for figuring out what caused this particular issue. Now, I'm not saying that we should all go out and use GraphQL for everything ever. There is a reason that REST is still incredibly popular, because it is, quite frankly, suitable for a vast majority of use cases. What I am saying is that if you're working with more complex data, or if you're working with evolving requirements, then GraphQL might be the correct tool for you to use in your scenario. So let's say you have a use case. You want to build a GraphQL API. How do we get started? First, let's look at it from the front-end point of view. Let's go consume ourselves a GraphQL API. To do this manually, you pick yourself your favorite API client. There are plenty of them out there, whether you're going with Postman or Apollo or Insomnia or another one that I've not included on the slide. It doesn't matter which one you go with, they all follow the same sort of structure, which is they will have an area for you to put in the URL for the endpoint that you're going to be querying. They have an area that displays the structure of the schema of the GraphQL API. And the reason it has this so early is because you need to know the structure of the schema to be able to determine the structure of the query itself. And you can retrieve the schema manually if you want to by running an introspective query, but having the client do it automatically is pretty nice. So your structure of your schema is the structure of your query, and also the structure of your query is the structure of your response. So whatever you want to put in is what you will get out in return, unless you want it to be something different, at which point we can do a few things within our queries in order to modify the response that we receive. So let's say, for example, this is a fairly okay structure. We're happy with most of it, but we might have used a different naming convention in the front-end UI. So even though there are two things that both essentially mean the name field, we're using different things and we've called it something else. So we could just send this through as it is and do some post-processing and update it and all of the fun stuff there. Or we could use an alias and have it done as part of the query, saving you that additional processing step. We could also use directives inside these queries in order to implement some basic logic. Now, there are a few default directives, including there's one for include, there's one for skip, which I don't know why it's not called exclude, there's one for deprecate, there's a few of them around. And you can make your own custom ones as well. And what they do is, in this particular scenario, this is essentially an if statement. So if the full details variable is set to true, then we want to include the model field within the response that we receive. So if we have the same API and set full details to false, then we have the query response without the model field. Nice and easy. Now, this one is, it's an okay query, like it's fine, it gets you the information that you want, how you want it. But in the same way that you can break an application down into components, you can break a query down into fragments. So here we've got a bit of duplication happening, just a little bit, mostly because there's not much space on a slide. And we want to extrapolate that out and just have that listed once and then called referentially. Now, if the vehicles and starships objects were both created from an overarching object type of transport, we could do something like this, where we just pull them out, put them in a fragment, and then refer to the fragment as we want. If we want to combine objects of different types, we can always also do that. We can do things like unions. So in this case, we've got a union of the person and planet objects, and if the name value is a person, we'll get the person data back. And if we have the same name value being a planet, we get the planet data back. So there's a lot of adaptability that you can have with the queries in order to get the returned response being exactly the structure that you need for your scenario. But it really, really depends on how you've built your schema. So you can only do the unions if you've got your schema set up to allow it. You can only do the fragments if it's based within the same overarch type. It's all very, very driven by how you design this. So let's swap over to building our GraphQL API. No surprises here. Your schema design is the first thing that you'll want to work on, and your schema is made up of several fairly basic parts. We start with the data structures. So all of the individual objects that you want to make available within this API, all of your things, you can have listed out here. And then based on those data structures, you can have your queries. And these are the ways in which you will allow front-end clients to call to retrieve data from your API. You can also have mutations, which are very similar to queries, but this time you're allowing people to modify APIs or to add data to your data sources. And then finally, we can also have subscriptions, which, to be honest, is essentially just keeping open a WebSocket connection. But what it does is it allows you to be alerted if there's any external changes to your data source's data. Now you pop that all together and you have yourself a schema. Nice. So then we get to the other half of the building, which is we build our resolvers. Now a resolver, much like the name suggests, it resolves things. In particular, it resolves individual fields and links. This is the part where you are linking to your data source and retrieving the information as required. Now, your data source can be anything. You could be going to a various number of databases, you could be going to another API, you could be going to a random text file on your machine. It does not care. It's quite happy to resolve from wherever you need it to. And the resolver functions have a very particular set of parameters that we need. So we've got 4 parameters: parents, args, context, and info. Now, parent is actually the result of the execution of the previous resolver. So yes, if it's the first resolver that's run, that is null. And the reason that we have that result is because we need to use it in two different ways. So first, we need to be able to keep track of what data goes where when we have the results of all of the resolvers functions, so that we can serialize them into a single file, which is usually JSON, and return that to the front-end client as the response. We can also use the parent as a data source. So say this query returns this book object, and then the next resolver that runs is for retrieving the author details. Because the parent parameter in this scenario is that book object, we can refer to the author ID within it and use it as a data source for retrieving our next set of information. Make sense? Excellent, got some nods. So that's parent. Then we have args, which you never believe this, it's short for arguments. And these are the arguments that were within your original query in the first place that you can use for including inside logic as needed. Then there's context, which these are your more global pieces of information. This is the same regardless of your resolver. And this is everything that it would need that is, well, contextual. So your authentication information for the user is always going to be the same. Or if you know that you're going to be connecting to particular databases and you just want to share the connection details more globally, this is also where that would be. And then finally you have info, which is your nice to have, additional, optional, etc. This is a great place for you to put any additional information, whether you want to do the path from root so that you can have it there for setting a caching policy at the resolver level, or just anything you like, really. And honestly, that is basically your resolver in a nutshell. So at this point, people start going, okay, so if you're letting all of the users do all of their queries on all of the parameters on a single endpoint or a minimal amount of endpoints, how does security work? And the cop-out answer is it works how you build it, in that there is a quite large number of ways and it's quite flexible and you can do what's useful for your scenario. For an actual answer, for authentication, I would recommend intercepting the requests before they get to the resolvers using middleware, and there are a number of standard libraries that will enable you to do that. So like Express JWT is one that shockingly is quite good at helping you validate your JSON web tokens, and you can authenticate your users that way. For your authorization, you can do any kind of logic you like. You can go role-based, you can go attribute-based, you can write your own logic. GraphQL does not care. All that I would recommend is that you abstract it outside of the resolvers and just have them call the authorization logic as needed so that you can have it all in the same place. But by applying it here, you get that greater level of granularity because you can apply it on a field-by-field level. And again, there are standard libraries for that, like GraphQL Shield. Now, GraphQL will let you do a lot of things, and sometimes it will let you do too much. It will give you a bit too much flexibility. And out of the box, you can put yourself at risk of a denial of service attack by having an overly complex query that exhausts all of your resources. So, for example, this is technically a valid query. It's a little recursive, but it will try to execute depending on the API, and if it's able to resolve, it will quite happily give you the JSON back in the same format. But you can see how with that level of complexity and that level of recursion, you could really crash and break everything quite easily. So we want to maybe consider not letting that happen. And there are a few different ways we can do this. We could have a threshold for the level of complexity that we are willing to accept for an input. And again, there are standard libraries, and again, they are called very obvious names like GraphQL Query Complexity Library to allow you to set that threshold easily, or you could limit things by depth, so you can choose how deep you're going to allow this query to be nested and prevent it being too complicated that way. Or you could do your rate limiting, or your pagination, or your caching, or any of your other more standard approaches that you would take to handling things in your REST APIs also apply to your GraphQL API. And then once you've got everything built, it's up and running, you might want to keep an eye on it. And there are observability tools available out there. There's GraphQL, there's Apollo Studio, and again, they're all fairly standard and they all have fairly similar features, and they will let you quite easily keep track of your logs and your matrices, and you're doing your traces in a nice, convenient format. So now that we know how to build a GraphQL API, surely all we want to do now is keep building more and more of them, right? Just keep going and keep building all of the GraphQL APIs forever. If you're doing that, what I would recommend is that you can actually integrate them together into using GraphQL Federation and have a unified API. And as an example of this, if you think of the Star Wars API, you could have one single overarching schema that has all of the data structures and all of the data that you need in it. Or you could have a sub-service that's for the characters, maybe you'll have one for planets, you could have another one for the films, and then you can integrate them all together in an API gateway, and it will still look like a single GraphQL API to your front-end clients. And what this allows you to do is you can work on each of these subgraphs and not worry about impacting the rest of the system. So you can scale them individually, or you can do whatever you like, and it's just a lot more modular and easy to maintain from a maintenance perspective. If you get too many APIs going, or too many subgraphs going, or if you get too complex because you've gone mad with power and you're creating all of these things, you can start having performance issues in the same way that you would have performance issues with anything after you overloaded it and built it and did all these cool things. And for this, Facebook has again created another thing. So Data Loader is a way of having your API calls batched and cached. So instead of having multiple calls to a particular data source for each of the individual resolvers and going open connection, get it, open connection, get it, close, instead of doing that, you can batch it all together and do a single connection, get the data you need, and get out. So it tidies things up quite nicely there. And it also keeps the returned data in cache, so that if you need it for any additional steps or any resolvers that are executing later on, they can retrieve it from there as a data source rather than making the call out again. Now, because we can't have a talk without AI, yes, you can stick AI in GraphQL. There are a few different ways that you could do this. You could use an AI API as a data source, or you could actually integrate AI into the building of your queries and your APIs in the first place. So GQLPT exists. And if you would like to, instead of structuring your own very simple query in the declarative language that's easy to use, you can just put in your question in natural language and have it generated for you. So GraphQL is a useful tool. Today we've learned that it was created because we needed to deal with a complex data scenario, and it handles that quite nicely. We know that if we're working with evolving data requirements, that again, it can be the right tool for the job. We've looked at how you consume it and how you structure your queries so that you can get the data sources as need be. And then we've looked a bit into building our GraphQL APIs including the security and the observability and everything to keep in mind for a successful GraphQL API to be created. And then we've created a whole load more and federated them, which is pretty fun. So with that, thank you all for listening. Here is the QR code again, and are there any questions?
Hi.
Hi.
Do you have any use cases for GraphQL that you've done at Bankwest?
I can, but I'm not allowed to talk about them.
Okay, that was my question.
Yeah, so for REST, you obviously have like post-patch updates and creates. Is there any analog with GraphQL?
In short, yes. In long, also yes. Yeah.
Yep, I'm walking.
So a question about access pattern design. In GraphQL, obviously, you can design your access patterns however you want, and it's very flexible. When you go to optimize those access patterns, how do you deal with that? Like if I've got a certain access pattern defined in a REST API, I can add an index to the database. Whereas in GraphQL, how do you account for that unknown of the access pattern?
I think I'm going to have to think about that and get back to you. I'm not sure, apart from a more standard answer of you just keep testing and keep trying and keep doing. But I don't have any specific answer for that, sorry.
Just wondering how does GraphQL handle like retries and other resilience kind of operations?
Yes, you can put in retries in there, and you can, any of your more async or retrying things can be built in the same way that you would build it for any other API. Do we have any more questions? Oh, we've got one down the front.
Thank you. Just one thing, or two things to mention. I think one of the best benefits of the GraphQL that I could see was the self-documentation.
Yes.
Which wasn't mentioned. The thing I didn't understand was the resolvers. So you mentioned query, mutations, and subscriptions. What with the resolver, you had the resolver inside the query. Is that? I didn't quite understand how that worked.
Okay, yeah. So first of all, yes, excellent shout out about the self-documentation. I had forgotten to mention that, and it is quite useful that you literally cannot have a GraphQL API that isn't documented. Score. With the resolvers, the way that it works is in your schema, you've defined particular queries that you're allowing it to use. So if you have a Star Wars API and you're allowing it to query based on character, then you have a list of essentially you can do character queries in the schema. And then in the resolver function is working by, for all of the available queries, when we are allowing them to search by character, then we are returning this resource for this character function. And then, so if you were retrieving your character information, you'll be pulling from this resolver. If you wanted to update a character, then it would be a different area of the resolver file, which would be under the mutations, which would be the character update mutation, and then you would have a different resolver for applying that update logic. Does that make more sense? Okay, cool. Thanks. Any more questions?
No, we are ready to go.
Awesome.
Oh, one more.
Can we wait for the microphone, please? I cannot hear you at all, I'm sorry.
Sorry.
In terms of just adapting GraphQL APIs, are there any advantages of just remaining with REST APIs?
Sure. So GraphQL is great for complex data, but it's also a bit more complex to set up in the first place. So if you don't need the functionality that GraphQL provides, if you can get the information you need quite easily through a REST API, then use a REST API. Like, you don't need to go overkill on it just because it's a cool tech to work with. It's more just, it's a tool that you can use depending on the scenario. No worries.
In your experience, have you ever migrated a REST API to a GraphQL API? And if so, or if not, can you think of any kind of pitfalls that you'd need to keep in mind?
So I haven't done it personally, so I am very much winging this now. If people are used to working with the individual endpoints and they're used to structuring things, like if they're used to having the security based on the endpoint or just used to having that separation of concerns, you could have a pitfall where you're not setting up your authentication and authorization properly for the new GraphQL API because they would be thinking endpoint rather than variable. So that might be something that I would be more worried about if I was doing that transformation. Thank you. Going once, going twice. All right, cool. Thank you very much.
Thank you, Rebecca. Okay, so there's a quick message from DDD team. Do everybody knows about a yearbook? Yeah? Yes or no? No, okay. Have you seen a yearbook before? Or do you have one at home? Okay, you have one at home. DDD, because this year is our 10 years anniversary, so we do have a yearbook, and it is $25, which equates to 4 or 5 coffee, depending on where you get it from. So anyways, you can, if you want, you can go and get it at the info desk.
This is
$25. That's right. And you can have friends at DDD write you memory notes in your yearbook. How cute is that? Don't know whose idea is it, but anyways, enjoy the rest of the conference.
Not sure if you've heard, but at Bankwest, we're on a mission to become Australia's favourite digital bank and to make banking seriously uncomplicated. Imagine digital banking so simple, it makes sense to everyone, no matter who they are or where they are.
That means me.
We know that uncomplicated doesn't just happen, it's made. Not by a company or one individual or even a bot. It's made through our curiosity, honesty, and desire for change.
In other words, it's made by us.
We know becoming the favourite isn't easy, but when you're making a difference for customers, colleagues, and the community, when you feel like you're learning and growing and your ambition is matched, well then, it's all worth it.
The truth is, Australians deserve easy, useful banking experiences. This mightn't sound like a big thing, but for us, it's everything.
It would take all of us working together
to make something we're all proud of.
And that's why we need brilliant people like you.
Bankwest, made by us.
MakerX is an award-winning research and development studio, building digital products and high-growth ventures at the frontier of technology. Our team of 40 experts, including 10 former CXOs, brings a wealth of industry insight and advanced expertise, including AI, Web3, and venture building. Combining an extensive library of robust technology building blocks, an entrepreneurial culture, and a proprietary R&D framework, we create groundbreaking products, open new markets for corporations, and optimize existing businesses. For those brave enough to do what's never been done, get in touch to discuss how MakerX can drive your business forward. For inventors passionate about fearless exploration and bold experimentation, MakerX offers a vibrant, inclusive environment where innovation and continuous learning are core principles. Here at MakerX, you'll work on transformative projects ranging from virtual machine compilers to nonprofit mental health apps. Join us to help invent the future and make a meaningful impact in the digital world. MakerX, made for tomorrow.
Hi, I'm Melissa Herrera from DataStax, a company focused on helping developers turn their dreams into wild new realities through generative AI. We are here to make it 100 times easier and faster for developers to build Gen AI and RAG, or Retrieval Augmented Generation, apps and experiences that you can quickly get into production. DataStax offers a one-stop Gen AI stack and data API that gives developers all the data to build a complete RAG app for a faster and easier path to production. We've also added Langflow, making it easy for developers to build one-click RAG at scale, with an open-source visual RAG framework with drag-and-drop data flows and pre-built components for connecting to any API, data source, or database, one-click deployment, and seamless integration with AstroDB for more relevant answers with ultra-low latency, giving you 20% higher relevance, 9 times more throughput, and 74 times faster response time at 80% better TCO. DataStax delivers a RAG-first developer experience with first-in-class integrations with leading AI ecosystem partners. So we just work with developers' existing stacks of choice.
Why is Mandel Group such a great place to be? Gee, that's hard. Where do you start?
Immediately what comes to mind is the people. Might sound like a cliche thing to say, but genuinely I believe that we've got the best people, not only technically and from a consulting perspective, but just generally as people.
Mantle Group principle that resonates most with me. I smile because there's a few, look, they actually all resonate with me, but I would say in it together.
Love what you do and be awesome at it. In my mind, people are at their most productive and engaged and enjoy their work the most when they're doing something that they're passionate about.
The Mantle Group principle that resonates most for me is make good choices. It's the fundamental one that sits almost underneath the other principles and allows us to use those principles to make our decisions and how we work.
Make good choices. I love this one because it's around treating people as an individual and trusting them to make a choice that's right for them.
We're close to 1,000 people now, and we still are able to be principle-based, where our team genuinely make good decisions and use their principles to guide themselves.
Mantle Group principles enable me to be more me at work.
We're breaking the mold in ensuring that we create an experience for people that is unique to them and really redefines what work means for people.
1, 2, 1, 2. 1, 2.
Hi, everyone. Hello. Hi. Wow. Why the energy so low? What's happening? 3:30. Well, good news is this is the last talk track of River Room 1, and after this is coffee break, which is pretty good. Okay, anyways, we have Graham Foster here today. He's going to talk about leveraging LLMs to build intelligent applications. LLM stands for large language model if people don't know what it means. So Graham is a technical specialist in apps at Microsoft. He's been writing code for 40 years. I wasn't born yet, 40 years. Anyways, he actually my colleagues, and he said that I can say this, okay? He said that I can write Python better than him. And his demo today is not Python at all. I don't even know what language he used. Please welcome Graham.
Cool, thank you, Gia. Everybody hear me okay? Yeah, awesome, brilliant. And thanks for sticking with us till this time as well. I know it's the last session of the day, so it's always a hard slog till here. So hopefully we can inject some really awesome LLM energy into this room this afternoon. So thanks to all the sponsors. Obviously, events like DDD Perth don't happen without all of these amazing companies helping us out. So huge thank you to everybody up on that screen today. That's my last slide. I don't like slides. So I don't like Python either. So okay. See, I did that. I said that exact thing at a Microsoft event 3 weeks ago. And I swear nobody in the room cracked a giggle at that. So I feel like I'm winning already. So I will be spending my time today help. Oh, we're back. Awesome, cool. I'm going to spend my time in LinkPad. This is C# code for those that aren't familiar with it. But don't worry too much because it's not going to get that complicated. Actually, it looks pretty complicated, doesn't it? Mental note to self. I've seen a lot of pop stars fall off stages in the last few weeks. There's a huge drop about 2 meters back from me here. And I like to move around on a stage. So I'm kind of hoping I don't fall off because Rob's got his video camera down there and he might actually record that. All right. So when I first did this talk about a year ago, some people hadn't heard of things like GPT and LLMs and stuff like that. But I mean, let's get a show of hands in the room to start with. Who has actually used a large language model like GPT or Gemini or Claude? This might be the quickest talk of your life then. There's other talks on today. Who's used them in anger? Who's got kind of serious with them? All right. Okay, cool. So, about a year ago when GPT first dropped, and everything I'm going to show you today is applicable to other large language models. It's not just the OpenAI ones. So everything here is kind of like across the board. But when GPT dropped, whenever it did, seems like a decade ago. I know it was only like a year ago. All of these frameworks started popping up around it. So you might have heard of things like LangChain, semantic kernel, there's Llama Index now, I'm getting a few nods in here. We have AutoGen, and everything looked magic, right? You kind of look at these things and you see the claims around them and you think, oh my God, like this, I don't understand it. And I don't know about you, but when I don't understand something, I kind of don't like that because people are asking me about it. Like, what does this thing do? How does it work? And if I don't know it, my natural instinct sometimes, and I don't know if this is a good trait or not, is to go back to the very basics and to actually just play with the APIs, the raw API calls, and then see what I can do with them. And what was interesting about GPT was the more I started to play with the API calls, the more I started to get an insight into what tools like LangChain and Semantic Kernel and AutoGen are actually doing under the hood. And the more you do that, the magic and mystique of those tools starts to disappear. I'm not saying that large language models aren't kind of like magic under the hood. We all saw the keynote this morning, and there's some crazy stuff going in there. But when you start to actually build on top of them, there's actually not much magic going on. So that's what I want to do today, is really take you through my little learning journey of really dispelling all of that magic from large language models, but getting a really good handle on what they do and how you can bring them into your own applications. And hopefully that'll give you some ideas of how you could take this technology and implement it in a sane way, right? As opposed to something that they're not really suitable for. So that's the plan. And we're going to do it for a series of little C# demonstrations that try and explain what's going on behind the hood. So with that, I'm going to start at the first demo, right? So at the end of the day, all large language models are just a simple REST API call away from you. And they all work on the same premise, in that you pass some text. We'll get into things like tokens and embeddings and stuff like that later. But you pass some text into them, and then you can pass a few little fiddle factors, like numbers that you can change to change the kind of output that the large language model is going to give you. And then the large language model will have a guess at probably the next most likely token, word, they're not quite the same, they're close enough, that might appear. And then it will push that back in. And given what you passed in and that new token, it will come up with another token, and then another token, and then another token, until finally it hits some kind of stop signal. That could be that you said, hey, I only want X amount of tokens, or it might just think, yeah, that's a good enough response. Everything you're going to see today is that, and it has some really kind of cool implications. So it starts off looking very simple, something like this. We talked about twiddle factors. Large language models have got a few key things that we can tweak. So we have a property called temperature. Raise the temperature really high and watch the output of a kind of open prompt. It's hilarious. The models get super excited. They're a bit like me after I've had a drink or two later on, if anyone is at the after-show party. And they come up with some crazy stuff. It's really good fun to watch. We've got this property called nucleus sampling factor. Basically, what did we say? It's an alternative to temperature. 0.1 means only the tokens comprising the top 10% probability will be output. Okay, we'll have a look at that in a minute. Max tokens. All large language models charge by tokens. You'll basically charge on the number of tokens you pass in and the number of tokens that you get out. So if you're smashing tens of thousands of these, you're going to get a really, really big bill if you've got a popular service. So think about keeping that down. Obviously, that's going to change the amount of output that you get. There's a few other things, frequency penalties, presence penalties. They all, again, just adjust that output. And then we have this thing called the deployment name. So in mine, I'm using GPT-4o. We all know there's a ton of models now, right? GPT-35, GPT-3, GPT-4, GPT-4 Vision. There's loads and loads and loads. So they're all trained in kind of to provide different capability outputs. At the end of the day, these models have pretty much consumed the entire content on the internet that's just being pushed into this huge neural network. And that's kind of what's going on, and very simplistic. Again, it was explained way better in the keynote earlier. But that's why large language models give kind of better responses on some things than they do to other things. Because really, the foundation models are all about what's the content out there on the training data. And they're really good at that. I saw one earlier about that maths test where it's like, yeah, 85% output on GPT-4o. Like, apparently, if you start to change some of the questions on that, then that really starts to drop quite significantly. So it makes you wonder about the training data sometimes. And then a really interesting one, log probabilities per token. So we then go to the actual prompts. And prompts really have got, let's say, 2 or 3 main components to them. The first is super important. It's called the system prompt. So this sets up the whole context for the operation or the interaction with the large language model. So you might have seen prompts where you say to a LLM things like, you are a pirate, you must respond like a pirate, or something kind of silly like that. And the point of the system prompt is that it's really kind of key to setting what that response is going to come out like. So without knowing the internals, it seems to have a much higher impact on the sort of output that you get. So you can see here, I'm going to tell my large language model, you're a poet. You create spellbinding, hilarious poems that are only 5 lines long in response to a prompt. So we've seeded that now. Everyone can see this at the back, can they, by the way? It's all good? Yep, perfect. And then we have the interactions. Now, we're using an API here called the Chat Completions API. Think of it as like modeling a conversation. We have the system prompt, and then we have the user saying something, that's me, and then we have the assistant, which is the large language model, will respond, and we can keep that conversation flowing. So in my case, I'm an engineer changing his demos on the fly in a live session. And then we can run that, and if all goes well, live demos. Dun, dun, dun. We get a huge amount of response back. Okay? So the important bit, and this comes back as JSON, on the far right-hand side, let's see if we can scroll on this one, is my little poem that I get back in a live demo, nerves on high, switching code with a hopeful sigh. That's kind of fun, actually. But one of the important things about large language models is we talked about tokens and how what's going on under the scenes is that instead of coming up with a single big response, the LLM is outputting a response token by token and then considering the last output, putting a new token onto it. So with this little log probabilities per token option, we can get interesting insight into that. So you can see for the first word in my poem, we had in. But there were a couple of possibilities the LLM chose from, in and with. And then let's have a look. We had the word live come out. That could have been straight up to room. We had demo come out, demo session. So that's kind of what's going on, right? Everything you're going to see from now on is just a variation on this. Right? If I can give you one little piece of wisdom, follow the prompts. If you're not sure how an LLM works, set up a reverse proxy, have a look at the prompts. Some of them will alarm you, some of them will surprise you, some of them will give you joy and pleasure to read, because it's quite incredible to see how we get the best responses out of these amazing large language models. But let's say you're trying to write an application, because that's what we're here to talk about today. Now, those of you that have built applications for a long time will know that this kind of input, that little poem that we had, is not the easiest thing to digest inside a computer program if you want to do something more with that output. Like if all you're trying to do is show something to the end user, happy days. But if I'm building an application and I want to do something more, let's say I'm building a bank teller application. So I want to have a conversation with a human being, right? And I want to know what it is they want to do today. So I've got rid of the prompt that I had earlier, which was probably a better one to have. Basically started saying, you're a bank teller. Let's go for this one. Tell me what the customer is trying to do. And we'll plug this one in, change on the fly, and then we'll have them say, what's my bank balance? That seems pretty good. See, I was changing my demos on the fly in a session. What have I done wrong? Oh, don't you love your string literals in C#? Damn it, why didn't we use Python for this? It would have been so much better. What's my bank balance? What's going to come out? All the way over here. The customer is trying to check their bank balance. Well, that's lovely, but how does a computer work on that? Now, what you'll find with large language models is that there's only a certain amount of input you can throw into them. So they all have these kind of prompt windows, maximum amounts of tokens that we can push through them. So to write an application, we start to have to think about, well, maybe, because we can't put everything in, large language models are a bit like people as well, even if you try and fill the token window, they're very good at remembering the top bit, and they're very good at remembering the end bit. But the stuff in the middle, which is probably like now for the next half an hour of my talk, will kind of disappear. And then you'll walk away at the end going, oh yeah, I remember the first 5 minutes. Python, .NET, something like that. What about the middle bit? So it's really impractical to just throw one prompt into an LLM and expect to get an output for your user. So we start to have to think about how can we actually tweak the large language model to give us things that we can actually use inside our control flow of our program. And this is how things like semantic kernel and LangChain are built together. They comprise of lots of small little prompts, and interactions with other systems, and they chain everything together and then give you an output. So the first thing we're going to do is we're going to take that prompt we just saw, and we're going to add one little extra piece to it. So we're going to tell it, actually, I don't want you to give a lovely, fluffy response back to me. I want a single phrase. In my case, I'm going to say, choose from the following intents, like intent detection. Are they interested in account information, new accounts, new credit cards, branch information? Now, I've got this little bit down here, an example and a response. We call this like single-shot learning or multi-shot learning. The idea is that inside our prompt, we give an example to the LLM. Again, it's kind of like if you're a human doing a task and you're not quite sure how to do it, if someone sort of says, oh, and if this happens, then you do that, and you go, oh, yeah, right, I kind of get the gist of it now. LLMs are like that. So now, if we run this prompt with what's my bank balance, we're going to get back, if all goes well, a phrase, account information, which, and it doesn't always happen, you can be very careful when you're testing large language models, is very likely, is very highly probable to be one of these, unless it doesn't know what it is. And in that case, if I say something like, where are the fish? And I've never worked as a bank teller, but I would hope people don't come in and say things like, where are the fish? Well, it's a bit small, that, isn't it? But in the context now, it's no idea what we're trying to do. So I don't know. I have no idea. So this is cool, right? So we started to look at a little prompt here. But this is no good on its own. We've taken the conversation, and what we need to do now is say, well, okay, let's start thinking about what we do next in our IT system. So we're going to introduce a little chain into our prompt. See, that's my mouse kind of slipping down on the thing there. It's always hard doing mouses on lecterns. But what we're going to say is, look, let's try and work out what the intent of the customer is. And then if, I'm not going to show you the C# code behind this because it doesn't really add any value at all. But it's a little if-then check. And we're just going to say, look, if the response is unknown, then let's keep this dialogue going. Let's prompt the user for more information. So this is our second little prompt. And in this one, the prompt is very similar to the first. You're a bank teller, you're trying to find the intent of the customer. What would you ask the customer next to find their intent, given their current input? Respond with just the question. Okay, so it's pretty straightforward. So if we run this one now, and we're going to pass in what is my account balance, then the response that comes back is great, account balance. We can work with that. We'll get to that in a minute. But if we don't know what the user's trying to do, and you're going to see this little debug thing going all the way through, then instead of getting an intent back, we get a suggested response. So if you think of a chatbot situation now, we've got this little bit of code that can use the LLM to work out what the customer's trying to do. If we know what they're trying to do, awesome, we'll get to that. But if we don't, then we're going to come up with a suggested response. So pretty easy so far, and you can see this is pretty good. Are you looking for information about your existing account? Or are you interested in opening a new account or a credit card? Which is awesome because this is all based off the intents that we have up there. Now, very simple one. So this is a long-running conversation. There's another key concept you're going to find in tools like LangChain and semantic kernel, and that's called memory. Memory is super straightforward. It's just this idea that we've probably got a stateless application, and we just need to retain this chat history somewhere. So we need to somehow store the conversation as it is. It tends to just get dumped in a database. There's nothing that complicated about it. There's only one thing I want to call out on here, and that's these conversations can get large over time. And because we have these finite-sized prompt windows, what you'll often see is that these tools like LangChain will have techniques to shrink the conversation history. So they kind of retain the essence of what's going on, but just kind of get rid of all the stuff that's not adding any value. So you can keep that token window for the really important things. So the bit here that's quite important, or probably more used to watch than the get intent of the memory, is the bit down the bottom. So you can see we've gone from this little dialogue, what do I want to do? Can you provide more specific information? Where can I catch a fish? And we've got the shrunk memory. The customer is seeking information on locations where they can go fishing. That's probably like a third the size or a quarter of the size of the conversation as it was. So memory, kind of, not really an LLM thing, but it's still really useful to know about. So we're going to move to the next key concept in large language models, which are called embeddings. So who's familiar with embeddings in here? Yeah, there's plenty of hands going up. There's quite a few not, though. All right. So I like to think of this in terms of a little example. Think of a word like cold, right? So let's take the word cold. Let's give it the number 1, okay? And let's think of the word hot. So we're going to take the word hot, and we're going to give that the number -1. Okay, so you see how I've kind of taken these two concepts, words at the moment, and we've turned them into two numbers, 1 and -1, which is great. Now, if you had something like freezing cold, like who could give me an idea of what number that might be? 2, you got 2. Okay, so freezing cold is 2. What about boiling hot? Again, it's going to be going the other way, right? -2. So what we're starting to do is we're starting to take words, language, concepts, semantics, and turn them into numbers that are related. Now, we could extrapolate on this, right? We could have a phrase like, I'm turning green, or a phrase like, I'm going green, right? Those are very similar words, but they have very different meanings. Turning green, going green. One is kind of saying, I'm going to be going green. I'm probably going to buy an EV. I'm going to, go off the grid, all that kind of stuff. But the other is, I'm turning green. Could be somebody at the party later on tonight, right? They're going to be really, really unrelated concepts. And if you look at the embeddings that get created, they're very different. Now, an embedding is more than one number. It's, depending on the model that you use, it can be like 1,500, something like that. But the basic idea is that we can take language and semantics and meaning, and we can feed that into a large language model, and we can turn it into a list of 1,500 numbers that capture the essence of what we've put into that prompt. And embeddings also have another pretty cool feature, which is that because they're coming out of the large language model and the LLM's been trained on all this data from the internet, there's a lot of different languages out there on the internet. It's not just English, right? So LLMs and embeddings are actually comparable across languages as well. So we have this kind of thing that can take text and meaning and semantics, and we can use images as well to calculate embeddings, which is also a pretty cool trick. And we can turn them into these long comparable lists of numbers. So it's, again, a pretty straightforward call to our LLM. We're just going to say get embeddings, and this is just the kind of output that you get, a huge list of numbers. But these have a little trick up their sleeve. Because vectors, it turns out, are comparable things. So if we put all of these in a database, so let's say we've got a book and we've got a whole bunch of vectors out of it, we put them in a database, and then the user comes along and they enter some text, we can now go to the database and say, look, we've got this bit of text here. Do you have anything that's similar to it? So in maths, they call it a cosine similarity search. And it's a super quick operation for finding text that looks similar, related to what we're trying to search over. So let's move on to number 6, I think we're up to. So this is the essence of a pattern called RAG. So anyone in here has heard of that? It stands for Retrieval Augmented Generation. And the idea is that because we can't put, again, the entire works of Shakespeare, let's say, into a single prompt, if we need to somehow search over that, or let's say it's our own corporate data, right? We need to search over our own corporate data. That's not in the foundation models. They know nothing about my procedures. They know nothing about my data. So if I can find a way to take my data and store it in a database, and then allow this kind of natural language similarity search over it, then I'm going to hopefully find something that's really relevant to help my customers. So think about searching unstructured data, corporate policy documents, that kind of thing. So the way we do it is we take these big documents and we start to snip them into what we call chunks. So when you want to talk to your data scientists, there's a real art in chunking documents. Simple techniques might just take like 100 words. You might find more complex techniques that can look at the documents and pull out metadata about images and graphs and things like that. And the whole point of this is it's like a pre-processing to be able to index our content in such a way that we can search over it later. So again, there's tons of ways you can approach it. Like, not all chunking strategies are the same. But the whole intent is to be able to get our embeddings in the database. And I've got a couple of documents that I've indexed, actually 2 very simple ones. Let's have a look ahead. And then I've done the text from Alice in Wonderland, like the story. So the first one, I had a very simple PDF file, and it just had some fictitious opening hours of a store. And we can search, we're just going to use Azure AI Search here, but again, you can use any database that's got vector indexes, so Postgres has got them now. I think most vendor-provided databases have got support for vectors, so it's pretty much a commodity thing. And we can see on my first search, what are the opening hours of our store on Monday? I get this huge chunk of information that's come back. And if you have a quick read of that, you'll notice that there is information about opening hours of stores. So all good. That's my first one that's worked. Let's go for what are the colors of the rainbow. And the document that this one fetches back is a very simple PDF file. Chunk 0 of the PDF file. The colors of the rainbow are red, orange, yellow, blah, 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 blah. I'll spare you all my French. I'm from Northern England. It's not a pleasant thing to listen to. But if we can throw a query in French, and I've tried this in Klingon as well, turns out there's actually half-decent support for Klingon out there on the internet. Who'd have thought it, right? So it comes out with pretty good results. But here you can go, like the colors of the rainbow are red, orange, yellow. One thing I've learned since I first did this talk, actually, Azure AI Search has got the concept of, they call it hybrid searching internally. So what that means is that it will not only search over embeddings, but it will search over text as well. And then internally, it will run a re-ranking algorithm and give you the best results based off embeddings and text. So if I was doing this demo now, and this is what I've seen most tools do today, is they actually ask the LLM to translate the text before they call the search engine. And then they pass the text in the language of the document. So then you get the best of both worlds. But if you've just got embeddings, then this is absolutely fine to do. Again, a couple more little examples. Let's go for where did the white rabbit live? So again, this has taken the whole Alice in Wonderland, and we've embedded that. And in this case, again, a lot of information in there, and it's found chunk 9 of Alice in Wonderland was the best chunk for that. But there's a ton of information in here, right? So this is not something that you could go and put back in the hands of the customer straight away, because even though the information might be in there, it's not exactly easy for them to find it. So the question is, what do we do? And it just so happens we have this very powerful natural language engine at our control. So what we do is we create another prompt. So again, this is why LangChain was called LangChain, is because it's all about chaining these little prompts together. And in this one, and we follow it down here, so we know the intent, and then if we detect, I think in this case that it's branch information, then we're going to do the search, and then we're going to call present results. And the prompt in this case, straightforward. This time we're seeding the LLM saying you're a summarizer. You need to extract the relevant information from the excerpt that you're given, and then look at the customer's question and answer it based off that content. And say unknown if you don't know how to answer it. That's quite important in LLMs as well. A really good tip one of my colleagues told me is that if you don't tell an LLM to respond with unknown if it doesn't know the answer, then it's very likely to hallucinate the answer, which is not a scenario you want to get into. So always put a stop criteria. And this bit here is super important. You must respond in the language the user asked the question in. I moved from 3.5 to 4.0, and the way that I phrased this, for some reason, always gave an answer in Spanish. I have no idea why. I asked it to tell me why, and it told me, when I said, tell me why you're giving the language you're giving the answer in, it then went back to English. It was like a Heisenberg in the system, so it was so difficult. I asked it, tell me why in the language you're answering the question in, to tell me why you're answering in that language. And eventually we got there, and it was just the phrasing inside the LLM. So testing is so important. Like if you can't just up the model in production from say 4 to 4.0, because that could have huge ramifications on the answers that come out. So always make sure you've got a really good kind of LLM ops pipeline in there to make sure that things are going to work if you up those models. Now in my case though, let's run this one. So we go, what time is my branch open on Friday? So we're going to detect the intent. We go and run the embeddings. We know it's a search. We search against the vector index. We pull up the answer. And now, from the document chunk, we get the suggested response. Your branch opens at, whoopsie, 8 a.m. on a Friday, which if we look in there, hopefully that's good. Friday, 8 a.m. to 1700. Now, again, like, there's a few more interesting prompts here. Where's my mouse gone? There it is. Awesome. So let's start with an obvious one in French. What time does the shop open on Friday? "8 a.m. le vendredi." So that's right, which is good. I know that one's right. The implications of this are huge, right? Because so many organizations have got people whose primary language is in English. So given the ability to take all of your content that's in English, create the embeddings, have a natural language search over it in the user's preferred language, and then even give a response in the preferred language is amazing, really. It's a very, very powerful tool that we've got here. And finally, in this one, and I'm going to take this one just for a bit of live, again, fun, and let's just pull up Google Translate. Google Translate. And let's see. Enter text, auto detect. I think. So Japanese to English. Mondays, the store opens at 9 a.m. I don't want to put the question in case the question says, like, when does the store open on Friday? Because that would be a little bit embarrassing, but I'm sure it wouldn't. And similarly, if we go back to the White Rabbit one, so let's go for the one before. If anyone here does speak Japanese and can confirm that that did ask on Monday, though, that would be pretty good. Where did the White Rabbit live? This one was more complicated because we pulled out a big chunk of information. We do the search, and we're told the White Rabbit lived in a neat little house with a bright glass plate on the door engraved with the name White Rabbit, which is awesome. I'm going to call this base rag. So Michelle Sanford, who's talking at the moment, and I did a talk a few days ago on a newer technique called graph rag. So one of the drawbacks you'll find with this method of doing rag, where you're basically running over the text and taking it chunk by chunk, is that to get a good response to the user, you need their answer to be in a single chunk of information. So that works really well for kind of pointed questions like I've done here. Where did the rabbit live? What time did the shops open on Monday? But if you start asking meta questions like, what are the key themes in this document, then this kind of rag is not going to cut it. Because at best, it's going to pull back 2 or 3 chunks of information from the entire document. And you can't get all the themes of the document from that. So techniques like graph rag, which we won't go into today, they're really worth looking into because they build this huge knowledge graph up front. It's like a graph database with nodes and edges. And then they use different techniques to try and find the answers to your queries, still using the LLMs, but by walking over these graphs and finding information that could be scattered all throughout the documents. But in our case, this is cool. So this is RAG. This is kind of searching over unstructured data. And all right, that's great. And it was one of the first early use cases of LLMs. But most organizations have been building APIs for the last 20 years or so, right? So we've all heard about the API economy. So many orgs have built thousands of APIs that unlock the company's information. So what would be really cool is to be able to integrate with those and create these natural language experiences so that we can have a chat, but in the background, be finding the information the user needs by calling our APIs. So that's the next thing that we're going to look at. This one is called function calling. So the idea behind function calling is that what we can do is we can take a whole bunch of APIs and we can create JSON schema definitions of those. So I've got a very simple one down here. It's just called get account information. So this is an API that exists in my organization today, and pretty straightforward. I've got a description. It gets bank account information, given an account number, and then there's different types of information that we can get about the account. What we can do is we can advertise these to the large language model and then ask it the customer's question. And if the large language model thinks that one of my APIs is going to be useful to help to get to the information, then it will tell me that. And then I can go and call that API and present the data back into the large language model to help answer the user's query. So we can pass in like a lot of different functions. They're more generic now. When I first did this was a new thing. It's called function calling. We refer to them as tools now. And tools can be other things as well as functions. So you might have seen examples where you have things like code interpreters. So you can get a large language model to create Python code. They're really good with Python code. The C# code, not always as good, so probably should have been in Python for those demos. But then we can take that Python code and we can throw it into an interpreter, get the result, and then pass that back into the LLM or straight back to the user if required. But the general gist of it is that we basically tell the large language model, here's a function, and then we're going to say, what's the balance on my account? Now, this one's quite interesting. On this one, what you'll see, and again, this was a change from 3.5 Turbo to 4.0 that threw me, first of all. With 3.5 Turbo, this would say, call the function, but I don't know what the parameters are. Whereas with 4.0, there's clearly some more training that's gone into it in the back end now, and it never comes back with the function call if it doesn't have the parameters, or if it knows you can't call it. So instead, it comes back with something that could be useful to ask the user. Could you please provide your account number so that I can retrieve the balance information for you? Now, if we've got all of the information that we need in there, what's the balance on account 1, 2, 3, 4, 5, 6, 7, 8, 9? Then what we get told by the LLM is, hey, go and call this function. And we can pass a whole bunch of functions into it. And what you'll find is that as you start feeding the results from the functions back in, then that might cause it to say, call this function, call that function. Or it might finally hit a point where it thinks it can answer the question. So what we end up with, and we'll bring it all together, is this big chain. It's comprised of about probably 3 or 4 different calls to LLMs, some embeddings, maybe some AI search, maybe some API calling, to allow us to detect the intent from our users. So in this case, what time is my branch open at? We're going to go down here. We're going to do RAG search. We're going to fetch embeddings, vector index, blah, 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 user sentiment, branch information, and finally we get down there. All the way through to calls like, what are the last few payments on my account? So this one's going to take a different path. It's going to detect that it can make use of account information in the API calls. And we can go and call the API, get the data, and similarly to with the search result, we can feed that back through the LLM. So there's another little prompt down here which says, present the API results. Again, just a prompt. You're a bank teller. You receive the following data in response to a user's ask. Format the data in a concise way to answer the user's query. You must respond in the language the user asks in. Okay, so we've now got searching over unstructured data. We've got the concept of long-running chat histories, so we can interact with our users. We can tap into all of our APIs. So this is looking pretty cool. But there's probably one big problem with all of this. And that's that the amount of code I've now got to do this is really getting quite large. So there's, I think, the helpers have been under, I normally hide the regions, but here we go. There's the helpers up here. We've got prompts. We're calling OpenAI, we've got more prompts, we've got all these tiny little building blocks of code that we need to make this stuff work and hang together. And if you had to do this for every single type of interaction you want to have with your users, that's going to become a nightmare, right? So this is just to get a little bit of information, but let's say we've got 500 business processes that we want to expose to our users. We don't want to have to codify every one of those to be able to make that work. So we're going to have a look. I'm running low on time, aren't we, actually? That's gone so quickly. into a really cool concept, which are called plans. So these first appeared in semantic kernel, but they're now in most of the LLM frameworks that you're going to use. And the general idea behind them is that what I've shown you is essentially a bunch of small little building blocks. So I've got API calls, I've got unstructured searches, I've got the ability to summarize things. So if I could take all of these little building blocks, and then I could say to the LLM, look, the user's trying to achieve this goal. I don't know how to do it, but I've got a bunch of things that I think can help us get there. Can you structure these for me in such a way that we can get the output for the user? Now, the first time I saw this prompt was in semantic kernel, and it is a crazy prompt. In semantic kernel, it's got all sorts of things about rewarding the LLM if it does well. LLMs do really better if you reward them. Like, I will give you $1,000 for every good result that you give me. Worse still, if you threaten an LLM, it will work really hard to give you a result. Probably like humans, it might not be the best result, but it's going to work really hard. But these are all the kind of little things you see come out if you follow the prompts. This one's a bit simpler. What I'm going to do is I'm going to ask it to output some JSON for me that will describe how to achieve the goal. I'm going to give it the user's goal, and I'm going to give it some skills that it has access to. So in my case, and LLMs are really good at understanding text. The more metadata you have, the better this is going to work. If you just give it the names of functions, it's far less likely to give you a good output. But this one, I can summarize content. I can search for branch information. These are all little skills that I have. I can get embeddings for text. I'm describing inputs and outputs. And then what I do at the end is with one-shot learning, I give it what that might look like. So I'm telling it, I need your output to look like this, basically. And then what we're going to do is we're going to set it to task. So let's go and give it a goal for the user. The user wants to know what time their branch will open at on Sunday. Now, this is pretty cool. None of the other stuff wasn't. This is actually really cool. So here we go. It thinks to do this, it's going to go and extract key terms from the function, and I've asked it to tell me why. Extract key terms from the user's question about branch opening times. Here's the inputs and here's the outputs. So we can start to now, using code, chain all of this stuff together on the fly if we want to. It's then going to decide to call the embeddings function. Generate embeddings for the extracted key terms from a search. Once it's done that, it's going to go and call the search branch information using generated embeddings. It's then going to get the result from that, and it's going to call the summarize content function. So this is so cool, right? I have not had to codify this process. I've just given the LLM the little building blocks and the goal of what the customer is trying to achieve, and it's worked to come up with these. Now, I'm not saying you should do this in production in real time, but this could be really good as kind of how do I create all of these little workflows? Well, I'll run them ahead of time. I'll come up with a bunch of goals that I think my users will have, and I'll get the LLM ahead of time to come up with the plans, because these are quite expensive. So that's like the recommendation if you're using something like semantic kernel, is to do it in that way. I've got another one here. I haven't run this one for like 6 months. I've no idea if this one's going to work or not. So I mean that. I have no idea. So what are we doing here? Get account details. Straight away, it's gone to call that. We asked for the balance on account 123. It's told me the input and the output. It hasn't summarized the output. We didn't ask it in the goal. Like, you must present the outputs nicely to the end user. That probably would have got the summarize call in. But this is the kind of thing that brings all of these building blocks together in a really powerful way, is the concept of plans. Now, there's one, how long do we have? I got 1 minute, is it? 1 minute. Agents. Everyone's talking about agents today. Agents sound super complicated. They're actually not. All an agent is think of like, if you're trying to achieve a complex task, you probably can't do it on your own. You're going to need a bunch of helpers, and those helpers will be specialized in different things. So agents are really just different large language model system prompts that retain their own threads, and maybe external tools that can help. An agent doesn't have to be an LLM. But the idea is that an agent framework will bring all of these together. It will basically ask a coordinator agent and say, we're trying to do this. What should we do? And the coordinator will say, you should go and speak to that agent that can, let's say, go and extract information from a database. You get the information. Hey, coordinator, we have this. I think you should speak to that agent. And with that coordination, we can solve really complex tasks, or we can solve really silly tasks. I've got a 2-agent system here that are playing a game of guess my number. Again, agents all work like this behind the scenes if you follow the prompts. You tell the agent what its job is. In my case, you've got the number 53. Agent 2 is going to try and guess it. And then if it guesses too high, say too high. Too low, say too low. And the format of your output must be who you are, who's the next agent to call, and what it is we're going to pass them. And then we have the second silly agent. The second silly agent is trying to guess agent 1's number. So we just tell it, like, a number's going to come in. You're going to try and guess a number. You will be told too high or too low. And then once you've come up with your guess at what it is, then we're going to pass that back to the other agent. So pretty straightforward. There are different ways you can set up agents, but the kind of ethos is this. They're both going to have their own separate conversation history, and then we can set them off. And when we run this one, here they go. Obviously, you will use agents for far more complicated things and trivial tasks like this, but this is the essence of all agent frameworks. Love it. And that's why you don't follow my prompts. So I got all the way through those demos until the very last one failed. Is it 52? It actually is 53, if I recall correctly, but that's okay. We almost got there. So look, that's the last demo that I've got for you. If I could give you one piece of advice with LLMs, it would be there is no magic outside those foundation models. Stick a reverse proxy, follow the prompts. Most of them are open source anyway, so you can go and see them. And they are super inventive. They will give you your own ideas on how to structure all of this stuff. And with that, go have fun with LLMs. Thank you, everybody. Cheers.
We won't have time for questions because the afternoon tea is ready now, and I know that we don't want to stand in between you and the food. Anyways, there's a yearbook, $25, which is at the help desk if you would like to get the yearbook for the 10-year anniversary for DDD. Thank you.
Thank you.